The following message is best viewed on an oscilloscope.
Great, thanks. I do like that jingle. I feel that every time I watch it on Zoom, I get to see slightly different frames. It's quite challenging for live video streaming. So, welcome everyone to the fourth Computing and Data Handling parallel track. We're track 14 in ICHEP this year. So we have a very interesting program this morning. We're looking at event generation and simulation in the first part of the session, and then we'll turn to machine learning in the middle section. And finally, we'll look at offline computing with 3 of the LHC experiments results to us. So we'll kick off the morning with Marco Rossi, who's going to tell us about PDF flow. So, Marco, take it away.
Yes, can you see the screen?
Yep.
Okay, great.
You want to put it full screen? Yeah, now it's good. Yeah.
Okay, fine. So good morning, everyone. This is PDF flow, hardware accelerating parton density access. I'd like to introduce the concept of parton distribution functions with a physical example. Here you have in the plot the diagram for proton-proton interactions at LHC. In particular, the Higgs boson production via gluon fusion channel. And QCD tells us how to compute the cross-section for this process via the formula of the convolution of 2 PDFs, FA and FB, that takes into account long-distance behavior of the physics with a parton level cross-section sigma hat. The 2 PDFs are functions of 2 arguments, x and q squared. X is the fraction of momentum of the parton, of the incoming parton, with respect to the parent proton, and q squared is a typical energy scale of the hard process. The evolution of the PDF with respect to q squared is driven by the famous Diglap equation, and as you know, PDFs are essential for theoretical calculation since they enter the calculation of the integral seen before. Modern PDFs are presented with uncertainty bands that could slow down the convolution equation. Then any improvement in modern algorithm is welcome and valuable in order to speed up the entire computation. LHC PDF6 is the state-of-the-art accessing tools for PDFs. It provides official PDF sets that are collections of TXT files that contains several versions of grids of points in the XQ square space for all the flavors for the incoming partons. An example here from the NNPDF collaboration, you see that just a finite number of points are presented in these files. So in order to access all the points in the XQ square space, some interpolation method is needed inside the grid range, as well for some extrapolation method outside the grid range. LHA PDF has a Python interface that allows one to create a PDF object and fixing a PID, namely a flavor for the incoming parton. It allows to query an XQ² point and return the corresponding value for the PDF. This LHA PDF6 algorithm is a sequentially algorithm. In fact, it takes into account this accessing of the PDF with a loop, with a for loop. But as you can see, each of these calculation is intrinsically parallel, so the query points are independent. We try to redesign the LHA PDF6 algorithm and present this PDF flow tool in order to speed up the entire PDF accessing process, querying not just points in the XQ² space, but arrays of different sizes. We have we introduced this Python interface that returns an array of values of correspondent Q² points for the PDF. And this could really benefit from hardware acceleration, namely running this on multi-threading GPUs and graphic processing units. In order to leverage this parallelization, we use the capabilities of the TensorFlow library, which is an end-to-end open source platform for machine learning produced by Google. It has a rich Python API library, and we ensure the compatibility of our tool with TensorFlow version 2. Also, the interesting point in using TensorFlow is that it manages automatically the placement of tensors, which are the basic objects manipulated by TensorFlow library, onto several platforms like CPUs and GPUs. So there's no need to go through specific codes directly programming on GPUs that could make the task harder. TensorFlow has two execution modes in version 2. The eager mode that takes every line of the code and compile and executes it within a Python, and a graph mode. We wanted to explore this graph mode option that was previously on TensorFlow 1, the default one. But in a TensorFlow 2 version, you have this TF function, which allow one to wrap the usual eager code. So one codes into the usual imperative way, but wrapping the block with the TF function decorator, this triggers a graph building. A graph, TensorFlow graph, is a set of operations, TensorFlow operation as nodes, as you can see in the picture, and they are connected by edges where flow tensors between them. The graph is really parallel and is really faster compared to the eager mode. And the only caveat to have in mind when triggering this process is that some time takes when building the first time the graph. So when calling the first time the code wrapped with the TF function. We implemented the PDF flow tool and tried to match the accuracy of the previous state-of-the-art algorithm, LHA PDF. We present here this accuracy test with these two plots, plotting the absolute relative difference and putting an acceptance error threshold of 10 to the minus 3, according to the Lecce PDF6 paper. In the left plot, you have some curves. In fact, there's only one with fixed Q values and varying continuously the X argument for the PDF. On the right one, on the right plot, you have the opposite situation where we fixed the X and changed the Q. As you can see here, you can see the other, especially on the left plot, you can see the other curves, because the match with the LHA PDF is almost perfect. We just have this low Q problem in the extrapolation algorithm. So not inside the grid, we are outside the grid given in the PDF sets. But yes, this is there are a small region where the absolute relative difference is above threshold, but this could be not so relevant, since these such low values of the energy scale are not frequently inspected by Monte Carlo integrators for high energy physics processes. The interesting point for PDF flow is the performance benchmark against LHA PDF. We run this benchmark querying a different number of points sequentially for LHA PDF and with a parallel approach for PDF flow. Here in the plot, in the main plot, you have different number of points from 10 to the 5th up to 10 to the 6th, so 1 million of an array of 1 million of points. And as you can see, PDF flow outperforms LHA PDF in performance times. In the lower right plot, you have the absolute relative difference of the timings, and we claim around a 72% of relative improvement. On this is run on CPU with the Intel i9 with 36 cores for both the two algorithms. More interestingly is the situation when we run PDF flow on GPU. Of course, LHA PDF could be run just on CPU, but here you see that the difference in terms of performance is dramatically improved. You have around a 98 best relative improvement, just as shown in the lower right plot. And we are really happy to see these improvements compared to the LHA PDF algorithm. We implemented also another feature for the PDF flow tool, which is the strong running coupling. In fact, alpha S is presented into PDF sets as a grid of points in the Q space. This could be seen as the one-dimensional problem of the task previously seen for the PDFs. And we claim an exact matching between the PDF flow and the LHA PDF analog interpolator. Here in the plot, you can see the how the strong running coupling changes with the Q argument. We implemented two physical examples in order to show the capabilities of PDF flow. The first is the single top production at leading order that is presented by this Feynman diagram here, which takes into account the process of QQ bar into B bar into and a top. For this process, we combined the PDF flow, so the accessing tool for PDFs, with Vegas Flow, which is a Monte Carlo integrator that has been presented yesterday by my colleague. and it relies on the same philosophy of PDF flow, so massive parallelization and usage and leveraging with the TensorFlow capabilities.
3 minutes, Marco.
Okay, yes, it's the last slide. In this slide, you have the speed comparison of PDF Flow plus Vegas Flow run on two different platforms, CPU and GPU. As you can see, the CPU Intel i9 takes around 5 seconds, and all the GPUs outperforms the CPU. The speed up range takes into account a factor of 7 to a factor of around 10 for these performance improvements. The second example is the vector boson fusion for the Higgs production at next to leading order. We are happy to say that this is the first physical example at next to leading order, all ported on GPU. So this is achieved with again with PDF Flow and Vegas Flow. In this plot on the right, we compare the performance on CPU for the state-of-the-art code at next to leading order, LHA PDF plus a 4-tant implementation of the Monte Carlo integrator that takes around 360 seconds on a consumer grade Intel i7 CPU. The situation is better for LHA PDF and Fortran code for a professional grade hardware on Intel i9, but is not optimal since it's outperformed by the GPU implementation of PDF Flow and Vegas Flow combined. Here, the speed up at next to leading order is around a factor of 8 for consumer grade with respect to the best setup for the GPUs, and a factor of 3 for the professional grade hardware. So in conclusion, we presented PDF Flow, which is the first GPU port for PDF interpolation. We benchmarked against LHA PDF 6 for performance and accuracy. We achieved a big speed up, around 100% on GPUs. We implemented the alpha strong running coupling interpolation and provided two application examples at either at leading order and next to leading order. We claim that Vegas Flow and PDF Flow outperform standard CPU algorithms for either consumer and professional grade GPUs. The code has been recently released, and so it's public and available at the GitHub repository of Entry PDF. Also, the DOI is available as this link, at this link. So let me thank my colleagues to contribute to this work, and all the people who's following this presentation. Thank you very much.
That's great. Thanks very much, Marco. So we're open for questions now. Andy has raised his hand. So anybody else that wants to ask a question, just raise your hand in Zoom. Andy, go ahead.
Hi. First of all, I think very nice to see this happening. Having the event generation as the obvious candidate on accelerated hardware appearing, I think this is great for the field. The obvious question to something like this is how likely is it to abstract the actual technology in the code, saying we know now AMD floods the market with GPUs, blah blah blah. How likely do you see that we find some sort of a let's say meta programming style that's the adaptation to different actually acceleration hardware is not so painful for us?
Well, yesterday, the colleague of mine presented Vegas Flow and pointed that the main drawback of this, the advantage that CPU code is that is around for a long time. So the codes and the documentations around are all for CPUs. But I would say that machine learning provided a big speed up in this for the usage of hardware acceleration platforms and providing some documentation. As you can see, I want to show you some code. With PDF Flow, here you have LHA PDF6. So the usual chart presented before. As you can see, you just have 4 lines of code, 4 or 5 lines of code. You have to declare a PDF and then query all the points with a for loop. With the PDF Flow, that's the same. You declare a PDF and then you use it with your interface. But
Right.
in order to create the interface, you have to just code as usual, because the TensorFlow library allow you to do that. You have to code as usual with your eager code, and then wrap everything with the TF function, and then the trick is done. So I would like to say that there's no such a pain in this port to GPUs with this TensorFlow, but maybe with other machine learning libraries. That's great, because you have to pay attention on maybe little things that runs in the good way on TensorFlow, but not other implementation stuff. You don't have to learn other programming languages too.
I see you kind of outsource the problem to TensorFlow.
I guess what we're all hoping is that Google will do the hard work for us of porting for AMD and Intel.
It worked with search engine, so why not with more?
Okay, thank you very much again, Marco, and interesting little discussion afterwards, but we better move on now.
Thank you very much.
Just while Remy is setting up for the next talk, let me just remind people that we also have Mattermost. I'll post the link again for people so we can continue discussion there. But let's move on. So Remy will talk to us about the ILD software tools and detector performance. So go ahead, Remy.
There, sorry, the sound. Hi. Yes, it's fine. You can see my slides.
Yes, all good from our side.
Okay, thanks. So, hi everyone. I'm happy to give this talk today on behalf of my collaboration, ILD. My name is Remy. I'm working for the Linear Collider community, and today I will present this software tools we have and detector performance we get with these tools. So about the software, I'm actually talking about ILC Soft. So this is our software stack for the Linear Collider studies. So it's been developed now since 20 years, almost. This is the software stack for ILC, but not only, it's used by other experiments. Namely, it's actually maintained by us at FLC, at DESY, with the FLC group, but also at CERN with the CLIP group. So on the right, you have this the picture, basically showing all the components we have inside, so generator to simulation, reconstruction, and analysis. And today I will cover simulation reconstruction within our framework. So the main components there, the core components are that I will present a little bit later. We have DD4HEP, very nice package on geometry description for simulation and reconstruction for us. LCIO package, which is our event data model and format, event format. And then we have Marlin, which is designed for the reconstruction based on LCIO. So starting with DD for HEP, that's the detector geometry package. You have the GitHub link there. It's a generic detector description for HEP. So it's a project that was started in the context of IDA 2020 and mainly steered by the linear community at the beginning. And then different experiments started to use it, and now it's developed by mainly by LHCP people, if I'm correct, and still a bit in the context of IDA, and will continue in the next IDA thingy. So it's used by plenty of experiments, and more actually experiments are using it and also developing on top of it and collaborating with us. So it's very one of the, for what I've seen, one of the most beautiful, I think, collaborating software example I've actually seen there. So in terms of software itself, is basically a single complete description of your detector, including and all of this for simulation, reconstruction, analysis, visualization. So you have the sketch on the right, as you can see. Basically, it's the concept of having one single source of geometry description for everything, and different interfaces on top for depending if you want to run simulation, construction, and so on. So you have this DDG4 package, which is built on top of Geant4 for the simulation. And what we use also here for the linear collider studies is DDREC, which gives basically a high-level view on the detector, namely to access number of layers, extents, materials of the detector itself. So about the ILD detector, it's the one of the detector on the force and collision point of ILC. So there's an archive link there, which it links to what we call the IDR, the interim design report of the ILD detector. So basically it describes what I'm talking about here. This implementation of the detector in our framework is very, very realistic. So we describe all materials, extents, services, gaps, cooling pipe, really everything inside. So for this this paper there, this report, we have actually studied different designs, and namely two designs based on the large and the small TPC radius and everything in the strings. This is what you can see on the top level plot there. And in there, we are not decided yet with the calorimeter options. So what we've done actually, it's quite unique, I think, in HEP. We've implemented in the simulation the 4 different calorimeter options at the same time. So this is what you can see on the bottom right. This is an example with the HCal. There we have the usual absorber in blue, and then instead of having all the PCBs, glues, and so on, and the sensitivity detector, we have the sensitivity detector of one HCal, but then we replaced everything else by another sensitivity detector. So basically what we do is that we simulate the 2 HCal at the same time. And we've done this for the HCal and for the ECal. And the table there is basically the different combinations on the left, the different combinations of the ECal and HCal you can have, leading to 4 options. So why do we do that? It's because then you can simulate one detector, full detector with 4 options within the same simulation. You save a lot of CPU by doing that, and you minimize also the storage. Then if you want to reconstruct something, you have to choose an option and just go with it. If you want to see a bit more about the ILD concept, there's a very nice talk that actually happened a few minutes ago in another session by Tomohiko on the ILD detector. So it's a link, you can click on it. So about our event data model, it's called LCIO for Linear Collider IO. It's the data handling for all the HEP workflow we have. So from Monte Carlo to data and reconstruction, analysis, and so on. So it's very robust. It was developed almost 20 years ago, and we still use it, almost kind of the same version as 20 years ago. It's very robust. It's a standalone library, so it's not based on root. It's really standalone. We use binary format, XDR, and ZLib compression. We have versioning of data inside, so very backward compatible format. And very recently, I've made it actually thread safe for multi-threading development. So one of the nice things we actually have in this framework, it's what we call LC relation. This is what you see on the right with the different objects we have inside. And this LC relation there, it's basically a link between all different objects type we have in our data model. And it's very convenient in particular to link objects from Monte Carlo to reconstruct it, because then you can study, you can basically cheat algorithms sometime and go back from Rico to MC very easily and compare quantities there. It's very nice what we've implemented there. The LCO content file is actually quite independent. It's user defined. Usually what we use is the format for a simulation, for reconstruction, and then the schemed version of it. In the context of the SNOMAS, also in US, we are actually working on a mini DST format for high-level analysis, in particular for theorists. For the reconstruction framework, we use Marlin. It's a very standard HEP even processing framework. It's based on LCIO, which has a strong focus on reconstruction analysis. So this is what you can see on the right, the working principle. So we describe a task list, basically a task being what we call the processor there. And yeah, it's the little boxes, digitization, tracking, and so on. So, and then we just read events from the file and process them in an ordered way and populate the event with new data step by step. So very recently, there was an effort to actually re-implement this framework towards a multi-threading usage also. It's called Marlin MT. Has been used in ICHEP actually a year ago. I'll talk now about the production system, because we've produced actually a lot of data recently. It's based on the Dirac grid system, which is basically a job management system, provide also a file catalog for us. In terms of the production system, this transformation system, which allows you to transform your data from simulation, reconstruction, and so on. So this is all in Python. And on top of that, we have a specific tools, which is called IC Dirac, which is the extension for the IC and the Calis VOs. And you will find there some specific application for LCsoft. It's operated and actually developed at CERN by the Click group. So we have a strong collaboration with them. And recently we have actually produced a lot of data for the ILD detector, namely at 500 GeV center of mass, and with the expected luminosity of 500 femtobarn, and produce almost 1 petabyte of data. So that's quite a lot. On the right, I've just put a plot there for information, basically showing that our simulation is basically taking twice CPU as our construction. Yeah. So I go now to our reconstruction chain for the ILD. You can find the configuration there on the GitHub link there. It's clickable. So basically what we do, we have this background overlay, digitization, tracking, particle flow, high-level recall. For the background overlay, this is mainly designed for really collision event, not single particle studies. So what we do is that we have different sources of backgrounds, namely gamma to low PT hadrons and plus and minus pairs going to mainly in our forward detector, not only maybe for the plus and minus pairs. And we overlay one bunch crossing of data on top of the physics event on the collision. So namely, we have something like one background event per collision, depending on in total with all the different backgrounds. So this is what we overlay on top of our data before the digitization, which actually does the NNDG calibration for every detector, the time integration for the electronics, and sometimes also depending on the detectors and the implementation of the digitizers. We also emulate some inefficiency and noise randomization. So it's very complete also here. For the tracking, we do this in 3 steps. So 3 independent steps. We have first in the vertex detector, we run the cellular automaton to find some candidate tracks. In the forward detector, we do some triplet search of seeds, and then we extrapolate with a kind of linear fit. Find some track candidates there also. And for the TPC, we look outside in the outer paths, do some clustering there, and then start there for the Kalman filter, see the first one, and then go backward. This is what you can see on the left, just illustration. Then we get basically 3 different set of tracks and then combine them, and we run a Kalman filter refit on top of that to have our final tracks. Then comes the next step, which is the particle flow, something which is really designed for our detectors there. So it's implemented by Pandora PFA, and basically we reconstruct particle individually, contrary to the standard approach in HEP physics. There we do some calorimeter clustering first, and then some pattern recognition association, because you have some energy deposit a bit there, and you want to associate correctly things. Then you get basically a full picture of your events, but then there can be some mistakes. So we have some iterative reclustering recovery. This is what you can see there on this picture. You can have a neutral hadron, for example, in the vicinity of a charged hadron there. So we just trigger a new algorithm locally and recluster the thing to get a proper track to cluster matching. When everything is done, we have some very straightforward particle identification, which provided this kind of this type there of particle IDs. On top of that, we have a more complete particle ID, which is based on the TPC DDX. Also, the shower shape is computed a little bit later after the particle flow, and everything is combined in a multivariate analysis. We also run some gamma finders. So basically we identify some different gammas and then do a kinematic fit to identify mainly pi zeros and eta particles. We have also a primary vertex finder, which is implemented in SCFI Plus and SCFI Vertex packages. And then we have also some estimate of time of flight using calorimeter heats, using fast timing calorimeters. So,
3 minutes, Remy.
Yeah, okay. For the ILD detector performance, we have, first I will talk about the tracking. So the goal for the central tracks in the barrel for the momentum is like 2 to the -5. This is what you can see on the left here, it's the red line. And namely, we really reach it correctly there. So we have very nice performance there. For the tracking efficiency, as you can see there, as a function of the momentum, we are basically at 1 all the time, and there's a little drop of efficiency, of course, if you do at very low momentum curves. Tracks are very curling there, and it's a bit complicated to reconstruct things correctly at some point. For the jet energy, this is the second thing we usually look at for the detector performance. We use specific samples, which are what we call Z at rest, basically Z without any kinematic energy, just decaying there with UDS jets back to back. And what we do is that we compute the total energy and divide it by 2. It's basically what we estimate as the jet energy for the detector performance. There, the goal is set up to have something like around 3 to 4%, and this is what you can see there on the left. We really reach this performance there. Of course, if you go in some specific region of the detector, namely in the forward direction there, this is what you can see here. This is really degrading. Of course, you have the beam pipe and a lot of gaps between different detectors. So we are a little bit worse there, but in the barrel region, mainly, this is what you have here. We are really reaching this performance. I go now to particle ID. Namely, what we have here is a TPC, so we use the DDX. And recently, what we've done in the context of this document I talked about, we included also some time of flight estimate using the ECAL heats and fast timing response of the detector. We have here the separation power, which is plotted on the right here. And what you can see is basically if you pick up the yellow line there and these 2 ones there and the red here, it's basically the combination with and without the time of flight estimate. And you can see at very low momentum, where normally the efficiency drops, the separation power drops there with the DDX only, you can nicely recover things with the TOF. So this is something we want to study more in the future. For the flavor tag, it's very crucial for some analysis, namely Higgs to CC bar and BB bar. This is what you have on the left here. BB bar on the left and CC bar on the right, and we use VDTs there, and As you can see, we have very nice likeliness for B's and C's, depending on what you study there. So very nice efficiencies. I come to my conclusion. So we have developed since many years the ICHEP software stack for future collider studies, namely for the IC for us. We use the IC Monte Carlo production system. And recently we have produced 1 petabyte of data for Monte Carlo studies. We have very excellent ILE performance, as I've shown also. And for the outlook, I would say that we are putting quite some effort also to make our software stack evolving towards a multi-threading usage. So it was actually my personal work also on this. Part of the tools that I've presented, namely SCIO, for example, is actually used as a basis for this project you might have heard about. It's Key4Hep, which is maybe the future frameworks for future experiments. And there's a lot of software that we actually share there, and we are very proud of it. For the reconstruction performance, there's of course still a lot of improvement to do. Namely, we have very nice detectors, but we don't yet fully exploit all the features of our detectors in the reconstruction. And namely, we want to investigate a little bit more on the fast timing side of the detectors. And there we can really improve things. Thanks a lot.
Thank you very much, Remy. So we've probably got time for one quick question. If somebody has one.
Yeah, can I ask a quick question, Graham?
Go ahead, Jason.
Yeah. So, Remy, you mentioned, thanks for your nice talk. I mean, you mentioned that this evolution towards multi-threading. Are you considering also offloading to accelerators or something like that? Do you have any plans or? Well, this could be good for reconstructing or tracking, something like that. For particle flow, I think that as there are some iterations, this is not very well suited. But anyway, I mean, do you plan for that?
So, so we are really early in our software, and basically we looked around what people did actually, and so it's very nice because we are a little bit late and we can actually watch what people are actually doing, and it's very nice to learn things quickly. So what we've started to do is first to have some parallel event processing. So that was our first step, namely to learn about all of this. Not sure we have, except that, yet another plan for acceleration. So mainly we are focusing on parallel event processing on the framework side. Then of course, that's also the beauty of the software there, because we are using collaborative software and everyone has its own solution for acceleration. So we can also take benefit of it. But for the ICSoft itself, it's mainly focused on parallel event processing in Mali.
Okay, thanks very much, Remy. And I do like the fact that you've used so many packages which are used widely across HIP. I think that's a real strong point of the ILD community. However, time escapes us, so we better move on to Tom, who's going to give us the next talk on spherical proportional counters. So take it away, Tom.
Okay, I'll get started, and I'll assume that you can see my slides and you can hear me okay. Please stop me if you can't. So yeah, a slight change now. I'm going to talk about simulation framework for spherical proportional counters. This is work we've been doing at the University of Birmingham for the people here. For those of you who don't know, what are spherical proportional counters? So spherical proportional counters, which I'll refer to as SPCs throughout this talk, are novel gaseous detectors with multiple potential applications. These include searching for dark matter, neutron spectroscopy, neutrino-less double beta decay, and other low-energy neutrino physics. So there's a wide range of uses for these detectors, and being able to simulate what happens in them is crucial for future detector design and for interpreting measured data. To put a picture in your mind what these detectors look like, so these aren't cathedral-sized detectors like we see at the LHC. These tend to be much, much smaller, but they're these metallic spheres. So you can see this one in the top left might be familiar to some of you. This is a former LEP RF cavity which is repurposed. This was the prototype SPC. And then we see several SPCs from around the world. The bottom two are owned by us at the University of Birmingham. The one on the right actually sits in one of the buildings at the university. Unfortunately, we've not been able to access it the past few months. And this photo on the bottom left was taken at Bulby Underground Laboratory, which is in Yorkshire in the UK, where we've set up a small R&D project with an SPC. So a quick overview about what these are. So you have a grounded metallic shell, as you saw on the previous slide, and inside this sphere, you fill it with gas, and then you have a central anode sensor. So you try and put an anode directly at the center of the sphere. You see in this diagram here, this is what the anode looks like. Of course, you have to support that by some rod, and this rod contains a high voltage wire, which creates a radial electric field inside the sphere. There's several advantages to this spherical shape. You have low capacitance, which is largely independent of the size of your detector. You can operate it at high pressure, and you have the optimal volume to surface ratio. Additionally, one nice thing about these SPCs is that it's very easy to swap the gas inside to suit your physics needs. So there's a variety of gases which are good for certain things, and I'll touch on that a bit later. So SPCs are essentially spherical time projection chambers. This is just how they work. So you have some ionizing particle which will enter into your gas, and that produces initial ionization electrons. These can, of course, further ionize the gas, producing more electrons. And then, as I said previously, we have this electric field, which causes the electrons to drift towards the center of the detector. Once they get very close to the anode, the electric field is strong enough to cause them to avalanche, and they produce many electron-ion pairs. These continue to drift, and the drift of these ions away from the anode and the electrons towards the anode induces a signal that we can read out, process, and store. So now onto our simulation framework. So what we've done is we've combined other pieces of software into a complete simulation of SPCs. So there's three main components that are used. We use Geant4 for simulating interactions of particles and radiation with matter. We use Garfield++, which is a package developed primarily for micropattern gas detectors. But we use this for simulating the electron-ion drift and for calculating our signal. So Garfield is a nice package which interfaces to several other things, such as HEED, SRIM, and magvolts. So HEED is for primary ionization, for delta electron calculations. SRIM is for the energy deposition of ions in matter, and magvolts is a gas properties program. And then we use a program called ANSYS, which is a finite element solver for electric field calculations. You can see an example of an electric field produced by ANSYS here. So this is a slice in the detector, and you see the features I showed on the previous slide. You see the supporting rod, the central anode where the electric field magnitude is strong, and then towards the edge of the detector it becomes weak. So our framework combines these toolkits along with some custom calculations to produce the full simulation of the detector. So I'll just step through each part of the simulation now. So the first thing we do is the initial particle tracking. So this is done with Geant4. So we can use the very useful particle gun class of Geant4 to produce our initial ionizing particles. This, of course, gives us complete flexibility about what we want to study. So we can choose what particle we want to study, what energy it has, where it starts, what direction, and so on. And this is really useful for mimicking calibration sources. So when you're calibrating an SPC, you typically put a radioactive source in. So if we had an alpha particle source, for example, we could place our particle gun where we put our source and fire alpha particles of a specific energy. One thing that we've added quite recently is the ability to use Geant4's radioactive decay physics model. This is really nice because it allows us to just put unstable isotopes in our detector and let Geant4 deal with the details of how those isotopes decay. So in this plot on the right, you see an example of 1000 argon-37 decays. Argon-37 is a typical calibration source. And you see that Geant4 deals with how many events decay via K-shell, electron capture, L-shell, and M-shell, and whether they give you Auger electrons or X-rays. So rather than having to simulate these 3 peaks separately and normalize the appropriate, normalize the contributions, you can just rely on the model to the point you trust it, of course. After you've produced your initial particle, we continue to track it with Geant4 until it produces electrons with energy of less than 2 keV. At that point, we switch over to using Garfield++. So Geant4 passes the information about where these electrons are to Garfield++, and that takes over. So the first thing is that Garfield uses heat to produce delta electrons. Another relatively new feature we added was the ability to use SRIM. So this is, as I briefly mentioned, this allows us to study the dE/dx of ions and matter. So we've added the support for alpha particles for SRIM. You see a plot on the right here of the number of initial electrons produced by a 5.3 MeV alpha particle, just to give you an idea of how many particles we're producing here. So this is a single alpha particle, well, many events, but just one alpha particle per event, and you get something like 204,000 initial electrons produced in your gas. Once you have these ionization electrons, what you want to do is you want to drift them towards the avalanche region. So that's the next step. So this is done using a combination of ANSYS, which gives us our electric field map, and magbolts, which gives us the properties of the gas we're using via the Garfield++ interfaces. So you see here some plots produced from magbolts showing a few properties of the gas, of a particular gas. So this is argon CH4, 2 different pressures. And you can see how various properties change as you increase the electric field strength. So as you increase the electric field strength, the drift velocity tends to increase, but the diffusion tends to decrease. So these are the transverse and longitudinal components, diffusion coefficients. So as the electric field strength gets stronger, diffusion decreases. So this diffusion is very important in the outer regions of the detector where the electric field strength is lower. Once we reach the central region of the detector, that's when the avalanche starts. So this is where the electrons produce many electron-ion pairs. Depending on exactly the properties of the detector, this process can produce several tens of thousands or even hundreds of thousands of electron-ion pairs. And if we were to track each individual electron-ion pair that was produced, this would become extremely computationally expensive. So for a single event, we'd have to track perhaps millions of individual electrons. So we don't do that. We use a bit of a trick. What we do, we parameterize the gain by numerically integrating the Townsend coefficient, which is shown in this top plot, minus the attachment coefficient, which is this bottom plot, along the path of each primary electron. So we still have to do this for, say, 200,000 electrons, like I showed a few slides ago, but we don't have to do it for 200 or 2 million electrons. So this is a time-saving trick. And once you've got this integral, you can use it to, you take the exponential to get that average gain, and that tells you how many electron-ion pairs were produced. And this follows a Polya distribution, so you just need to calculate the average gain, draw a random number, and then you found out how many electron-ion pairs you have. Your output from your simulation is a voltage pulse. So this is shown by this pinkish line here. This is a typical pulse that you would see in your experiment. Often in the experiment, they deconvolve that to a current pulse, which is shown by this purple negative pulse. In the simulation, of course, we have direct access to both of these. What you would typically do in an analysis is look at some properties of each of these pulses and reduce them down to single numbers. So typical things that I'll show include the integral of the pulse or the maximum amplitude of the pulse, which are useful for particle ID, but also the rise time of the pulse, which we define as the time it takes to go from 10% of the pulse maximum amplitude to 90% of the pulse maximum amplitude. So this allows us to distinguish different types of events in our detector. And I've demonstrated that in the first real use case here on slide 12, which is neutron spectroscopy. So SPCs can be used as neutron spectrometers if you fill them with nitrogen gas. If you do that, you have two main processes that occur. So you have a neutron interacts with a nitrogen nucleus to give you carbon and a proton, or neutron interacts with nitrogen to give you boron and an alpha particle. And it's these proton and alpha particles which interact with the gas in our detector and produce tracks. So you can use, if you see at the bottom here, this is kind of a walkthrough of what's happening. So on the left plot here, we have many events overlaid. So each event typically just has a single track in. Here we have a neutron beam coming in from the right, traveling along this orange line. And these teal colored lines are the tracks left by alpha particles, which tend to be very short. And the pink lines are tracks left by protons, which tend to be much longer. So if you were able to distinguish long tracks from short tracks, you'd be able to distinguish whether the proton interaction or the alpha interaction had occurred.
At 3 minutes, Tom.
Yeah, okay, great. Okay, and you can do that by looking at the properties of the pulse. So you see that these short alpha tracks, all their energy is deposited in the detector. You get very large pulses. Protons, you tend to get smaller pulses. And then if you take some of these individual properties of each of these lines to say, look at the pulse integral on the x-axis and the rise time on the y-axis, you see that you really nicely separate out these different types of events. So alpha events have a large integral and low rise time. Proton events have a low integral and high rise time. And these elastic scattering events have a low integral and low rise time. So you can use that to determine what occurred. The second use case I'll talk about is the R2D2 experiment. So this is an R&D project aiming to use an SPC to search for neutrinoless double beta decay. So we recently worked with that collaboration, providing some simulation of their detector. So what they were doing was calibrating or investigating the energy resolution of a detector. So they had a 40 centimeter diameter SPC filled with argon and methane, and they had an alpha particle source. And they put that alpha particle source in the detector and then looked at the energy resolution. You see this plot in the top right is a histogram, a 2D histogram of the data. So the x-axis here is actually the integral of the current, which they call QT, and dt is the duration of the current pulse. And you can see they get a peak of events here at a single integral value, and then they get this tail of events coming down here. So we were able to simulate this, and you see our simulation in the bottom right-hand plot here. Rather than a histogram now, we just have a scatter plot where the point represents the direction the alpha particle traveled. And you can see that as the direction of the alpha particle changes, its position on this plot changes. So these events in this peak region are where the entire alpha particle track is contained within the detector. And then at this tail, these are when the alpha particle tracks hit the wall of the detector and you lose some of their energy and don't record it. But you see the agreement here is quite nice. The final use case I'll talk about is something that's being investigated by the NEWS-G collaboration, which is searching for dark matter. So they've been looking at a new type of anode. sensor. So traditionally, as I showed at the start, SPCs have single anode sensors, but recently progress has been made in using multiple anode sensors. So these are called Akinos sensors. Akinos is the Greek word for sea urchin, and you can see from this picture down here why they've chosen that name. What this essentially allows you is to read out multiple channels from your event. So what we've done so far is look at simulating 2 readouts. So you read out the top 6 anodes and the bottom 5 anodes, and you get 2 pulses now to deal with. What you can do with that is constructing a symmetry to give you some directional information about whereabouts in your detector your interaction occurred. So I think I'm out of time now, so I'll just go to the summary. So we've developed a simulation framework for these SPCs, and they allow us to study them in some detail. SPCs are a very versatile detector, allowing us to search for many different types of physics, so dark matter, neutrino double beta decay, and neutron spectroscopy. We're now starting to see comparisons of our simulation with data, and so far we see good agreement. But we're continuing to work with a variety of different experiments and provide simulation for them. So there's a few other talks that have already happened, so you can go and watch them on YouTube. I'll put the links here. So to the R2D2 results, neutron spectroscopy, and NewsG. And I've also just put a link to our paper that we wrote about this here on the right. Thanks.
Great, thank you very much, Tom. That was very interesting. So we're kind of on time, but I think we can afford to take a question or two if people have them. Okay, if there's nothing from anybody else, I was going to ask actually about the field. I got the impression that you use ANSYS to solve the electric field equations inside the detector. And I was wondering if actually during the event when you're counting particles and avalanches are going on, do you actually have to take into account the avalanche's effect on the electric field?
So at the moment we don't do that, but that is something that can have an impact, and that's something that we will be investigating in the future. So you get an effect where that you've got a lot of charge in a specific region of your detector, and that can distort the electric field in that region.
Okay, that's interesting. I mean, what's the sort of, I would guess for a typical, it depends on the size, but for a typical one of these devices, what is the kind of time that it takes from for the charge to drift, avalanche, and be detected?
Yes, it's of order seconds for the full thing to happen. But yes, of course, it does depend on the size. So these aren't huge beasts, but they are growing. So this is a little sketch of the different sizes. The largest one currently in operation is Snow Globe, which is at Snow Lab in Canada. That's going to be used for searching for dark matter. So that's 140 centimeters in diameter, and of course the drift time in this detector is much larger than a 30 centimeter sphere like we just have for R&D at Birmingham.
Super, thanks very much. I don't see anything else, so that's great. I think then we can go to our first break, and we will resume at, well, 9:20 if you're in European time, 8:20 if you're in UK time, and adjust for your time zone accordingly. So thanks to the 3 speakers in the first session today, and let's say we'll resume in about 18 minutes. Okay, and I see that Martin has come, who's also speaking in the next session, so I think we can do a quick connection test. Everyone else can go off and do their kettle. But,
Hi, yeah, can you hear me?
Yeah, your audio is very good, Martin. Thank you.
Perfect. The video as well?
Yes, super.
Wonderful. And now the slides. Here you go.
Yep, they look great. Just try changing to another slide. That's super. Yeah.
Wonderful. Okay.
Excellent. Everything's very good. Okay, thanks a lot.
Okay, see you later.
Okay, we go properly to the break now.
Definitely.
Davide, maybe you could set up your slides and we can be ready to go off sharply at 20 past.
Yeah, sure. Okay. Can you see them, right?
Yeah.
Okay.
Go full screen.
Just let me select the pointer. Okay. Okay, great. Can you also see my pointer, right?
Yes, yeah, it's very useful.
Okay. Yeah.
Okay, well, welcome back from the break, everybody. The next section of the session today, we turn towards machine learning. So first of all, we're going to hear from Davide about quantum-inspired machine learning on high-energy physics data. So I'll turn over to you, Davide, and let you begin.
Okay, thank you very much. So good morning, everyone. I'm really glad to give this talk. I will show you some recent results on the last work that we did, which is titled Quantum-Inspired Machine Learning on High-Energy Physics Data. This work was done by the ICHEP Padova group in collaboration with the Quantum Information Group from the University of Padova. This is the outline, so I will briefly describe the physics case that we studied and the tool that we used, which is the three-tensor network. Then I will describe the work and the results that we achieved, and then I will draw some conclusions. So at CLSCB, we're interested in identifying jets, which are produced by heavy flavor quarks, namely B and C quarks. And the technique that we use is the so-called jet flavor tagging. In particular, for our physics case, we have considered B jet flavor tagging. So basically tag jets generated by B quarks. Why do we want to do that? Well, we would like to distinguish jets that are produced from B and anti-B quarks, and this is a fundamental technique because it enables us to measure the BB bar charge symmetry, which is defined here, where delta Y is the difference in pseudo-rapidity. And also, the symmetry is sensitive to new physics processes, so that's why it's so important to measure it with a really great precision. In round one, the B-jet flavor tagging has been performed with the muon tagging approach. So basically, you search for the highest transfer momentum muon inside the jet, and the charge of the muon is related through a semi-leptonic decay to the charge of the quark that has generated the jet. And here is the link to the result to the round one. This has been doing also for the round two. But as you know, recently machine learning algorithms have been developed to solve high-energy physics problems. And the paradigm here is different because the whole jet substructure is used as input. So you just select some variables of the jet substructure and you use them as input for your algorithm. So the situation is basically this one. So here is a sketch of an event at LHCb where I kind of highlight the two jets. And this is what has already been done. So you take your neural network, you take your machine learning algorithm, you select your input and you get some prediction, some output. And here actually what we have done in our work. So we are considering the so-called tensor networks. Why would we like to change this paradigm? Basically, because we would like to solve, let's say, some open problems on machine learning. One is to understand what the algorithm is doing. So, for example, we would like to consider and to measure the correlations between the features, between the input variables that we use in the algorithm. And we would like also to perform some real-time applications. So, as you may know, going to the next rounds of LHC, we would need some prediction time of around nanoseconds. So this is quite a challenge. So let me present what is a three-tensor network, which is the tool that we have used in this work. So tensor networks actually are a mathematical tool used to investigate quantum many-body systems on classical computers. And this relies on an efficient representation of quantum wave function. And this is achieved actually by approximizing a higher order tensor by a set of lower order tensors, which follows a typical geometry. So this is the main idea. So here you have your whole tensor describing your wave function, and you just go through a contraction of low-order tensors, as you can see here. And this is obtained basically by using some, let's say, typical operations with tensor. So you can contract, you can reshape, and you can factorize. Tensor. Not only you can do this, but you can also tune, you can also control the approximation via the so-called bond dimension, chi. So here you see, for example, that the whole tensor has 2 to the n parameters, so it's a huge tensor. By using this tensor network approximation, you see that the numbers of parameters change dramatically, and it is controlled by the bond dimension. Basically, the bond dimension is the dimension of the contracted indices between the tensors. And the greater the bond dimension, of course, the better the approximation, but of course also, let's say, the huge will be the computational time, as we will see, to compute this tensor. And as I said, you can use several geometries. I would say that the most famous one is the metric product state here, which resembles one chain of spins, but there are several actually. Here in our work, we have used the so-called tree tensor network. As you can see, it has this kind of tree shape. Tree tensor networks are useful to do some supervised machine learning problems. And as you know, a typical machine learning problem starts from a data samples, X, which are encoded in a dimensional feature space via a feature map. Then you also have your weight tensor, and this contraction describes your decision function. Here, we select this kind of feature map, which is actually a product of n local feature maps. And each of these feature maps is described in the following way. So basically, each feature, x of I, is represented, I would say, by a quantum spin. So here is, let's say, the quantum inspiration. Okay. And the output of your algorithm is actually a probability for that kind of sample to be of one class of another. So here's the probability. So this is the flow. So you have your raw data, you have this mapping to spins. So here's the quantum inspired thing. Then you go to your tensor network, which has been trained and evaluated, and then you have your prediction. So here's the flow that we have followed. So let me describe our work and our results. So we started from some Monte Carlo samples from ADCB Open Data. We used BB bar digest events at 13 TeV, so basically around 2 conditions. And we applied some kinematic cuts on the transfer momentum, on the pseudo rapidity, and we require both jets to contain a secondary vertex, the so-called SV tagging. Inside each jet, we select these particles, so muons, electrons, pions, kaons, and protons, and we select the ones with the highest transfer momentum. And for each of these particles, we select 3 variables: the charge, Q, the transfer momentum relative to the jet axis, and the distance between the particle and the jet axis in the eta phi space. Okay. As a final variable, we select the jet charge defined in the following way. So we are selecting 16 variables for each jet to describe the jet substructure. So we are using a so-called inclusive jet tagging algorithm. In the picture here, you can see the difference from the standard tagging algorithm, which relies on one single particle, and the inclusive tagging that we have used here. Then we used a tensor network and a deep neural network as classifiers. As I said, the output of these classifiers is a probability, which is defined actually in the following way. If the probability is greater than 0.5, the jet is classified to be generated by a B quark, and vice versa for an anti-B quark. Our figure of merit, so what we would like to, let's say, maximize, what we would like to see, to study, is the so-called tagging power, epsilon tag, which actually says how many jets are tagged correctly. So you see, it's obtained by by a product of the efficiency, so how many jets are actually classified, times this factor which relies on the accuracy, which is the fraction of jets that are correctly classified. The performances of these two classifiers are compared with each other and are compared with the standard muon tagging approach. And of course, since we would like to maximize the tagging power, we apply some cuts on the distribution probability in order to maximize it. So here are some results. On the left, you see the tagging power as a function of the jet transfer momentum. So you see that both algorithms, both the DNN and the tensor network, outperform the standard muon tagging by a factor of 10. We obtain better performances at lower jet transfer momentum. But the really interesting thing is that both the tensor network and the deep neural network have similar performances, as you can see here. Moreover, you can see that the output of the two classifiers are greatly correlated, as you can see in the plot on the right. So here I'm plotting the probability for the DNN and the TTN for B and B bar quarks. So you see that there is a great correlation. And we also perform some tests on physical variables, so the distribution of transfer momentum and the eta, in order to check for biases, and we haven't found them. So this is great. Going further, actually, we see that the distribution probabilities are rather different. So here is the distribution probability for the tensor network and from the deep neural network. You see that they are, despite their similar performances, the two distribution probabilities are totally different. So here you can also see the cuts that we have applied in order to maximize the tagging power. And the interesting thing here is that the tensor network is actually able to spot the presence of muon inside the jet. So here these peaks at 0 and 1 actually say that we have a great confidence in tagging a jet to be generated by an NTB or a B quark. Okay. And since these two plots here in the bottom, the black ones, are the one where a muon is found inside the jet, we can see that the tensor network actually can spot the presence of a muon, while actually the deep neural network doesn't have this confidence, these confident predictions. We went further because we would like also to measure correlation. So we would like to understand the relations between the features, between the input that we've used. And here, since the tensor network relies on this quantum approach, we can measure correlation and entanglement and entropy. So for example, if two features are highly correlated, is it possible to neglect at least one of them? And if the entropy of the set of features is low, then all the features coming from that set can be discarded, okay? This algorithm that performs this kind of selections is called quantum information post-learning feature selection. And in this way, from the 16 variables of the jet, we select just the 8 most important variables. Not only this, but as I said, also time, also the prediction times plays an important role. And here, the key point is that we can, let's say, have better prediction time, have better performances in timing by truncating the tensor network without retraining it. So this algorithm, which is called the quantum information adaptive network optimization, allows you to train the tensor network to a maximum bond dimension that you choose, okay? After the training, you can truncate the tensor network by simply lower the bond dimension. As I said, the bond dimension is the dimension that controls, let's say, the approximation of the general tensor. And we will see that actually the critical amount of information is kept. But the truncating tensor network can classify your data in a lower computational time, as you can see in the graph here. You see that there is a direct proportionality between the bond dimension chi and the prediction time. So we applied both the QIPS algorithm and the Quiano algorithm, and we obtained some significant results. So first of all, on the left, you see that by just applying the QIPS algorithm, so just by selecting the best eight features, we see that we lose only 1% of accuracy. Okay, so this algorithm, as I said, allows you to select the most relevant features for the prediction. So we don't lose too much accuracy here. While when applying also the Quiano algorithms for both the complete model, so the one with 16 features, and for the best 8, so the one with 8 features, we can lower the prediction time from 345 microseconds to 37 microseconds, so almost a factor of 10. And if we apply both the two algorithms, so we select the best 8 features and then we truncate the bond dimension in order to lower the prediction time, we can also reach 19 microseconds of prediction time while still maintaining, as you can see here, compatible accuracy with the complete model. This was done also, which was done only using one core of CPU. So planning to parallelize this on GPUs, we are pretty much confident that we will obtain a speed up of a factor around 10 to 100. So that's really interesting. Okay, so let me come to the conclusion. So we know that new machine learning algorithms are actually required to analyze LHC data, particularly in future runs where we would have challenging environment. And we have just proved that tree tensor networks are actually a suited method to solve some supervised machine learning problems, such as the jet flavor tagging. We have comparable performances with respect to the deep neural network. And of course, we are outperforming the standard jet tagging algorithm, but we can measure correlation and entropy between the input variables in order to select the most relevant features. And we can also lower the prediction time by just truncating the tensor network after the training. So for the future, we would like to study more complex tasks. For example, tagging jets generated by B and C works. That's really interesting. And we would also like to perform some real-time applications. So that's all from my side. Yeah, thank you very much for your attention.
Super, thanks very much, Davide. So let me open to questions. You can just raise your hand in Zoom. Well, let me jump in and ask one. You said that one of the nice things about this method was that you can make the prediction comprehensible. Somehow you can get more insight into what the network is doing. Now, I see that you use the network to identify which are the important variables, but do you get some insight into the way that the network processes and correlates the variables with this method as opposed to the DNN?
Yeah, actually we had some insights about this. Let me just go through. Okay, I have this one. So here, for example, you can see what happens actually by selecting just a few features from some variables. So you see, for example, here that the muon and the kaon plays an important role in the tagging power. Okay, so this comes basically from the physics. And if we go back to this graph here, I'm showing the correlation between the features. Actually, the features are ordered from 1 to 16, and the entropy here. So here, if I remember well, are the features from the kaon and the muon. So what I get here from the tensor network is that the kaon and the muon features are really important in defining, in classifying jets. So basically, I'm getting some insights on the physics that's going under this event. Yeah.
Okay. And if I understand correctly, it's really the way that you can sort of truncate this method much more easily than taking a DNN, removing a variable, retraining the entire thing. It's It's much faster to do.
Yeah, that's let's say the most interesting aspect, the fact that you don't need to retrain your network, but you can just truncate it. Actually, what we found is that, let's say that you want to train a network, a tensor network with bond dimension 10, okay, and then get your prediction. Actually, what you get is that if you train your network with a bond dimension 200, and then you truncate it to 10, you get better prediction performances than just training directly to bond dimension equal 10. Okay, so that's the interesting thing. You can train, let's say, whatever you want, whatever you like, and then you can truncate and still get accuracy, good accuracy, but lower prediction times, really lower.
Yeah. Okay, that's extremely interesting. Any last questions?
I need to jump into that. So I think if you train it to 100 dimensions and then truncate it, I think what you give, at least in my head, what I understand is you allow the network to actually have in this more multi-dimensional space to get a better, let's say, eigen representation of the internal correlations, right? And then you cut out the best ones. Yeah. Then you truncate. So I think that's actually very clever.
Mm-hmm.
Yeah, that's actually a very, let's say, powerful tool to use because I mean, you can. It's kind of a trade-off because you can choose, let's say, a too much higher bond dimension, because otherwise you get, of course, a better approximation, but it requires a lot of time to train. But still, if you let's say have a trade-off in the training part, then you can do some really good stuff on the prediction part. So yeah.
Excellent.
Very clever, like that.
Yeah. Thanks, Davide. So we better move on. So Andy is actually the next speaker. So he's going to be telling us about the TrackML challenge that people will know around.
Here we go. Let's do this. I think we're all set up, right?
Yep, go.
Okay. Yeah, I'll give the conclusion of the TrackML challenge. I think it's going to be our rather last big conference talk. So I'm going to talk you through the challenge and the main solutions and a few findings which we did with that. So I think that's actually the outline. So from the organization, we ran this challenge in 2 phases on 2 different platforms, all within 2018. And we had different focuses on the 2 challenges or 2 parts of the challenge, which I will tell you afterwards a bit more in detail. And we were composed as a good mix from LHC experiments and machine learning experts to set this up. And we also have some summary publications of these two challenges to come. Now, this would not have been possible without our sponsors. On slide 3, you will see that we gave the winners some prize money and we needed some infrastructure. And we were very grateful to have a set of sponsors actually helping us in this. Now, the challenge itself was concerning particle tracking, and I'm not going to go into details. That's the CMS detector, but it's just the innermost part of the tracker, and the aim was to find trajectories from particles, digested in a way that non-community experts could participate. So that took quite a long time in the making. What was the motivation behind that? Particle tracking per se is almost a simple thing. If you have low multiplicity, you have it on the left side here. The hits from one particle in the magnetic field, which is constant, are even spottable by eye. If you increase the luminosity, and at the bottom you see the interaction region basically from run 1 with around 5 pileup to the ultimate scenario, if it ever happened, FDFCCHH with around 1000, it gets more and more complicated. And as it does, it scales also in time like this. Now, this is just a illustration. It's a highly nonlinear scaling in processing this with classical algorithms. And I leave it to you to look up at the experiments. They are different scaling plots, which are updated constantly due to the fact that the experiments are putting, as we also saw before, quite a lot of work in trying to optimize this. Now, for the challenge, we needed a detector, so we came up with a virtual detector, the TrackML detector. I'll walk you very quickly through classical collision experiment detector, 4 pixel barrel layers centrally with disks at the end, then enclosed by a short strip system that defined the coverage to some eta coverage to 3. We did not expand to eta 4 as the phase 2 detectors will go, because we wanted to compare to, let's say, our known best algorithms, and then followed or finalized by a long strip detector. All in all, such that we had some realistic but optimistic material budget. You see the thickness of the detector at the bottom. And in this virtual detector, we simulated HL-LHC type events with a TT-bar signal event overlaid with a 200 average 200 pileup. You see the PT distribution. We used a fast track simulation of the ACTS package. All in all, that came to about 10,000 particles and 100,000 hits per event. So that's the ballpark numbers. We quasi-realistically digitized this by using a geometric approach, that you had non-Gaussian hit residuals. You see some examples for the pixels there, just to make it, let's say, not a toy example to solve. And this we prepared into a data set in CSV format in order to allow people from entirely outside the field to digest this. So this is just some structure. You would have all the hits labeled. You will have details about the hits. If you look on a pixelated module, for instance, you could get the cluster shapes. You can even get the charge deposition inside the cluster. And this is connected for the training data set with a huge truth file, where you basically could look up the ground truth. Where did this hit come from? That's what the hits look like. And then the challenge was to find connected hits, so a labeled set of hits, which would then qualify as one track. And the idea was, can you find all these tracks? So a solution would be a labeled set of hits, and we would that would be submitted as a CSV file to the platform with the ground truth at the for the evaluation data set at the platform. We'd apply some scoring, and then that would rank you in the challenge. The scoring was taken a lot from what we're using at LHC experiments, but modified and simplified. So we practically just did give a final score, which was the sum over all events, the sum over all tracks, then a weight for the track. You can see the weight function at the bottom at the left, where we would like to just encourage to have high PT tracks, to encourage a bit more the signal event. And then within the tracks, this was basically composed as the hit sum, and the hit sum was done such that we favored mostly the innermost hits and the outermost for track completion, and give 0 weight for unmatched hits. So the optimal score is 1. You got everything right. And the teams would submit, we would evaluate, and then we'll come with an online leaderboard. And once the time is up, you would get some substantial prize money, which you can see here, which was kindly given to us by the sponsors. So that's the outline. Now let's look into phase 1. How did phase 1 go? This was performed, let's say, halfway through 2018 with a 100 days open window to submit your solutions. And if you now look at the score evolution, this is the days from the start of the challenge versus the best score of the 100 best teams. You can actually see how this evolved, and you can see that immediately. So we gave a starting kit that gave a score, a really low score of about 20%. You can almost read that as 20% tracking efficiency. It's not entirely correct due to the weighting. But you can see how high of how fast the score developed. And at the end, we had roughly 700 or 650 teams submitting with the final score of 0.92, which is an amazing score to quote with. Now let's go through the final leaderboards. This is the final leaderboard. The final leaderboard was done as a private leaderboard on events that have never been seen, and also the leaderboard was never visible to the private leaderboard was never visible to the contestants, in order not to encourage submissions to basically do statistical improvements on your score. So we did a lot of care on that. Let's go quickly through the winning solution. Number one, phase one, a non-HEP member who made an algorithm that was a mixture between a classical pattern recognition algorithm with some pruning and some track cleaning that was done with scikit-learn, with starting from pairs of hits and then basically extending that. And that gave the winning solution with quite a substantial wall time. If you see 7 minutes per event, but at the first phase, we did not ask for the speed of the algorithms. That was followed up closely by another non-HEP member, which was a pure ML approach that used Python and Keras, that basically created a massive deep network with you see 4,000 input layers, 2,000 with 4,000 first hidden layers connected to 2,000 other hidden nodes in the layer, using all the input features and training basically a relationship between hits with the probability are those hits from one track, with a massive training effort. And then in the prediction reconstruction, basically unraveling this, take hit pairs, judge the probability that they belong together, and then build tracks from that. That worked extremely well, but the execution day, due to the loop overall pairs, is let's put it roughly 1 day per event. I'll put it there. And this then was followed up by our third position, which is Sergey, who's a member of our community, of the HEP community, that has written a classical approach of combinatorial so seeding and track following with a track model, and gained the third prize with that. Then we had some additional prizes. We gave an innovation prize from the jury. We had the juries assembled together. We had one prize that looked at only clustering solution. We had a deep learning prize and an organizer's pick. And just to give you an idea about the deep learning prize, this was Liam and Nicole Finney, who wrote actually RNN solution where they trained an RNN by giving I give you 5 hits, which were obtained by simple DB scan clustering, and then used a recurrent neural network to predict the next 5 hits. And that gave them the 7th place. But since this was such a unique way to look at it, we decided to award them the deep learning prize. A little bit aftermath of the phase one is, did we do well in the score? So we looked at the score stability, and we were very pleased to see that. You see here the score quartiles and extrema of the submitted solutions. So there was really no fluctuation or statistical problem to rank the contestants according to the score, which gave us quite a good confidence that we picked that correct. And we looked whether the score actually resembles some physics quantities, and yes, it did. So you can see here the top solutions, and you can also see how they compare to tracking efficiency. So on the left, you see basically tracking efficiency versus different detector or track quantities, and you can actually see that high score means high tracking efficiency. So the score actually resembled physics. We'll also try to digest a little bit what are the difficult, the different track classifications of or types that people found, and that's very interesting. You can see there is a few really outstanding solutions, and that led us to look a little bit how these solutions internally are correlated. So this is the next slide on 30. You see practically how close different solutions are when you just take the solution submissions and check the correlation distance. It's quite interesting that number 1 and number 2, who have done different solutions, are also here separated from the classical HEP solutions. So number 3 and number 4 were classical HEP solutions. So it tells us that by running different algorithms, you can see a different type of the event. So I think that's a really nice outcome of that. Now let's move to the second phase, which was the same, repeating this phase, this challenge, but looking at the speed of the algorithm as well. For this, we augmented the score we had in the first phase with an execution time, and to do that, we had to really work with the CodaLab team to create a setup where we basically have the event in memory, have a public API to call for the users, and then measure in a controlled environment the user executable. This is one of the first challenges where this has actually been done. Now let's look at the score evolution in phase 2. You can see basically how this runs along. One thing you see is there's way less submissions. We would have plotted more if we had way more. I'll come to this later. But you see how the scores basically approach. And if you look at the final score map, there's an extremely interesting correlation. You can see that the fastest solution are also the most accurate one, except for one outlier. And this I think should tell you something. If you do something right, you're fast at it. Final leaderboard from the 650 in the first phase. For the second round, only 7 teams made the cut, meaning they either didn't time out or have been at least above 0 in accuracy. This tells us also something, that the solution to our problem is so difficult that the entry level for doing that filters out a lot of people. Very quickly through the solutions, I don't have to say a lot because a lot of this have been taken on solutions from the phase 1, and I think this is also very interesting and good about the challenge, that people, either the same authors or you will see different authors, pick up solutions from another phase and modify them. The winning solution was Sergey, who came 3rd in phase 1. He took the same algorithm, ran it iteratively 80 times, and wrote a massive parameter optimization. So he optimized the roughly 10,000 parameters in order to not do any wrong lookups, etc. And he sped up his algorithm to become into a Hertz level, which is an amazing achievement. So less than a Hertz is running half a second for this. Phase 2 is also a HEP member. He is a rather similar solution in terms of combinatorial approach, but with a very nice addition. It basically builds a graph, and then to estimate whether the hit is great or not, it traverses the graph with a Kalman filter. And this is also extremely fast. Was about 1 second per event with the same accuracy. And the third solution, and that's the last one I present here, is actually someone who took the winning solution of phase 1, looked at the slow parts and replaced them with a direct ecliptic graph solution, which was pre-trained in the neural network doublet and triplet finder, and fed it back into the algorithm, and won the 3rd prize on that. Key lessons, my last slide, on phase 1, huge interest in and outside the community. Of course, the reputation of Kaggle as a platform helped. It was good that we took a lot of time in having the score defined, and we saw that the HEP code is or remains more than competitive, and people with the domain knowledge actually had a boost. And phase 2, we saw the entry barrier was high. Probably too high, but that's the problem. And I think that's good to spot out also. And we also see that the HEP code is currently the best we have, but alternative solutions are not lacking too far behind. Few spin-offs of this. The data set is now used all over the place in R&D projects, from quantum computing to more ML learning, etc. We are evolving this detector into an open data detector project that is in the finalization of validating, and then we want to have a data set which is even more realistic for people to train. And we certainly have built up a community which you can see by following basically follow-up workshops, etc., seminar talks. My conclusions for this project: it was great to work on it. Took us quite some years from the initial idea to have it executed, and it ran very successfully. We had a huge resonance in and outside the field. We connected the data science ML community with the HEP tracking community. Would we have seen more ML solution? Probably, but I think that's the picture right now in reconstruction machine learning. We are there where this is a runner-up system. I'm not going to be replaced by a robot next year, but who knows? And we'll have some spin-off that remains from it. Thank you.
Great, thanks very much, Andy. So we probably could have time for a quick couple of questions. Who want to raise their hands or just speak up? So Andy, assuming you haven't actually been replaced by a robot already, and with all of these Zoom meetings, who knows? I wonder, do you think that there's sort of ongoing interest from outside our community? You talked about the open data and the detector model. Is this something that we can continue to sort of attract ideas from the outside of HEP?
Yes, and there is one component which I have not mentioned here, would belong into another session, like the outreach session. It also has a huge educational and outreach potential. I mean, you can imagine having this sort of data set prepared for universities, and like learn and also teach event reconstruction and at an earlier stage, right? And I think that's also one addition. There is also professional interest on that. Data sets, complex data sets, are interesting for companies to test the algorithms. Yeah, and we're constantly in contact with people who say, can we use this, blah blah blah. Yeah.
Yeah, great. Okay. So I don't see any more hands up, and time is running away from us. So let's move on, and we'll change topic a little bit. So Martin is going to tell us about detecting erratic server behavior using machine learning. So take it away, Martin.
So hello, I hope you can hear me well. I'm Martin. I'll be talking about erratic server detection behavior. So we'll be talking about operation efficiency for a bit now, but we'll stay with machine learning. So this was a project I did in cooperation with the CERN IT, and I would like to thank them in advance. Anyway, the topic of this project was, if you have a history of a run of a distributed application, or of the cluster of servers that's running the application, is it possible to detect an erratic server within the cluster only by looking at the OS level metrics that were collected? Now, by OS level metrics, I'm talking about the CPU utilization, the memory usage, and so on and so forth. So this is what we'll be talking now. Now, the goals of this project was first to gather a data set, because we found out that there is no data set that could actually help us answer this question. And then there was to train the machine learning model on the data and see whether it actually works and whether this hypothesis is correct, or whether we cannot do that. So first, about gathering the data set. What the data set had to have. So it was supposed to be consisted of OS metrics from a cluster of hopefully equal servers, so there won't be any problems that we don't know about. And all the servers should be running some load balanced application. So the idea was that all the servers should behave more or less the same. The metrics in the data set were supposed to be easily correlated, so if, we can detect more advanced anomalies, and then obviously to capture some anomalies for us to detect. Now, for gathering the data set, we were using the CERN Monit, which is a monitoring infrastructure that's used by the CERN IT department. And as you can see on this image, it's rather complex, but we will be using only this, let's say, walk through the whole architecture. So the OS metrics are collected by the collectd daemon, then they are stored in the Kafka cluster, which you can imagine is like a 72-hour cache. They can be enriched and aggregated using the Spark distributed computing engine, and then they were stored in HDFS, from which we were doing the analysis of the metrics using Swan and then again Spark. Now, the collectd metrics in the Monit are not in a great format, as you see. So you have the host name, then you have the type of the metric in text, and then you have the value and the timestamp. Sadly, this is not great for correlation, right? So even worse is that the individual plugins on a host don't report at the same time. So you can have CPU reported at 1 minute and then the memory usage reported at another minute, and something can happen during that time. And obviously it's not synchronized over the whole cluster. So that was bad. So the first thing we did was we aggregated those metrics on a 20-minute time window, which was fixed. I mean, the time windows were fixed along the whole cluster. So we had something something rigid, and then we joined the individual metrics on the time window and on the host name, forming this long vector of metrics, which somehow represented the status of the host during those 20 minutes. The aggregation also provided some whitening, which was good. And yeah, so this was the input data for the algorithms. And if I refer to something as a server status snapshot, this is what I'm meaning. Now, this aggregation and joining was done using 2 Spark streaming jobs in the monitor infrastructure, obviously. The first one was doing the aggregation. The second one was doing the joining. Now, why I'm saying is that this was quite compute intensive, because the sheer amount of collectd metrics in the Monit infrastructure, it's about 13 megabytes per second throughput. So the aggregation job had to scan through all of this, do the uncompression, aggregation, and then output. So we had to run quite a hefty streaming job. It took around 25, 30 CPUs, and it consumed about 120 gigs of RAM. So this was actually quite a task. Then the joining job, it was a bit simpler. It only took about 10 gigs of RAM, but it had to keep a lot of status because it was joining all the different metric streams. So it was quite a challenge. Now, the anomalies. So first we thought that we'll just be analyzing the anomalies that occur naturally in the data. But it turns out that with the application that we chose, which was the Kafka streaming service, which is quite a well load balanced application, there are not that many anomalies taking place. So we actually decided to create our own anomalies. Now, we thought of 4 kinds of anomalies. First one was to stop the service altogether. Second one was simulating some sort of a memory leak. The fourth one was simulating some sort of loop stuck or something like that. So it was just overusing the CPU. And then the last one was just combining both anomalies together, simulating some sort of, let's say, virus or something which is consuming resources without the admin actually knowing about that. Now you can see the anomaly counts that we were able to capture are not as high as we would like. Initially, we were aiming at least 10 anomalies per type. Turns out that no one wants to let you screw up their servers in production. So we had to use a testing cluster, but the testing cluster was for testing. So there were not that many times that the testing cluster was actually running stably, which we needed to, you know, to simulate stable production, right? Anyway, we captured 26 anomalies. They were spread over 19 days. So sometimes we inserted 2 anomalies per day. But essentially, even if we meddled with the cluster, the operations were still rather smooth. And each of the sequence of anomalies were preceded by about 3 days of stable operations, which we used to train the models, but more about that later. Now, in terms of the metric count, we first hand selected 10 metrics from the selection, but later we just said, oh, okay, let's collect all of them and see how the algorithms do. So later we collected all 36 of the metrics. Now to the data analytics. First, we needed to do some pre-processing because even 10 metrics can be a bit too much for some of the algorithms. So and also we knew that some of the metrics are correlated. So we looked at the principal component analysis, or PCA. Here are the explain variances per component of PCAs. We say, okay, if we go with 3 or in some cases 5 metrics, we will capture most of the information that is indeed in the data while getting rid of a huge chunk of the space. So from now on, when I'll be talking about PCA reduced dimensions, I'll be talking about only 3 dimensions, which was nice, and the algorithms ran a bit better. Now, first we tried to do some unsupervised learning. First, we did some clustering, which is just automatic grouping of points together within some sort of intelligent algorithm. Now, this worked rather well when there was indeed an anomaly in the day. So we can see that okay, these points are somehow anomalous and they are grouped together. But when there was no anomaly, we didn't really knew how to detect that, right? Because the points were split more or less equally, and then they were switching back and forth. And yeah, we didn't really knew how to move forward. So we looked at some novelty detection algorithms. This is some like nugget finding and, you know, exactly the thing that we were trying to do. So we used some scikit-learn implemented algorithms, and you can see the precision and recall here. Now, the precision isn't even 80%, which is bad, because the one thing we don't want to do is present the operators with some false positives. Now, the recall isn't great either. So if you can manage to catch only 30% of the anomalies, it's not pretty good. But we can see what type of algorithms might work better in the future. And by future, I mean supervised learning. So by supervised learning, we mean that the algorithm gets some input data and tries to output some something that you actually tell him to, right? And this is how you train the algorithm. Now, we didn't want it to do a pure classification, meaning we didn't want it to, you know, present the algorithm, okay, this is a status snapshot and it's erratic, and this is a status snapshot and it's not erratic, because then we will train the algorithm only to recognize the anomalies that we created. And what do we know? Maybe they are completely, well, not completely, but we just didn't want it to do that, right? So what we thought of doing instead was giving the algorithms a couple of statuses from the history of the run of the specific server and let it predict the next status, right? Now, as you remember, the status snapshot is a vector of some metrics, which is 3 when we use PCA, or 10 or 36 when we don't use it. Sadly, we had to train algorithm model per model for each of them. So to do this prediction, you had to train a lot of models. Now, to give the model some idea about what's happening in the cluster, we also pasted together the status of the current server with the status average of the cluster, as you can see here, and let the model do its best. Now, we looked at 3 models. The baseline was just to say, okay, so the predicted statuses was the last one we saw. And since the operations were rather stable, it actually worked quite well. Then we tried to use a linear regression, which is just a linear combination of the outputs, which actually, again, stable operations, so worked pretty well as well. And then we used the random forest regressor, which is a combined output of many decision trees to produce the prediction. This was just to see how a more complicated algorithm will do. Now, because the input data space was quite large, we were restricted by the offers of the Spark ML library to do this. So this is why we went with those algorithms that you can see here. Now, okay, so we have the prediction, but how do we get the anomaly, right? So what we thought about was we will compare the predicted status with the actual status that we see and compute a prediction error. From that, we see whether the point is actually anomalous or not. Now, here you can see how the prediction error changes. This is when the anomaly started here and then here. Note that this is for the baseline algorithm, so the initial spike is not that big, and then interestingly, we have quite a big spike at the end of the anomaly, and I will talk about it a bit later. For the random forest regressor, which is a bit which is much more advanced, you can see that the first peak is a bit wider, which is good, and then the second peak is a bit lower, but it's still there. Now we actually
3 minutes, Martin.
Okay, we actually it turns out that this is exactly what you expect, right? Because when you take out the server from the cluster, it has to somehow update its status, right? So in the end of the anomaly, it actually does a lot of work. Now, fine, this is then to be expected. So how do we get a Boolean, whether that was anomalous or not? We said, okay, we will say that something is anomaly if the mean error for that data point is larger than if the error is larger than the mean error over the errors, and then 3 times the deviance. So this is your classic 3 sigma rule. Now, if we apply this algorithm at the example that I showed you earlier, you see that it quite well captures the anomaly there. But we also have some false positives, which are from other hosts, which were probably updating our anomalous host with the data that it has to catch up with. So we said, okay, let's say that we will count this as anomaly only if the algorithm classifies it as such twice in a row. Thus, we get a bit of a retardation, but we also get 0 false positives, which was amazing. In terms of recall, we saw about 70% recall with PCA, and then we also did a random forest run without PCA on all the 36 metrics. And we saw a recall of 78% there, which we said is quite actually good. We were really happy about that. Now, a bit interesting here is that we could see which of the metrics were important to the to the classification and which were not. So CPU idle, running process load, and CPU system were the most important, and some of the others didn't contribute to the classification at all. Now, in the future, if this were to use in production, we would have to automatize the training, because at the moment I was doing the training manually, and especially selecting the times where the cluster was running stable by hand and then training the model then. We would also have to port the algorithms to do anomaly detection on streaming data. And we will have to improve the stability of the streaming jobs, because they were quite large and the stability wasn't great. I had to keep an eye on the run more or less all the time. Now, it's the end of my presentation. I would like to thank the ITCM MM and especially Luca Magnoni with all the help that he gave me. And it's time for questions.
Super. Thanks very much, Martin. So questions?
Yeah, if I can make one question. As you know, as a co-host, I cannot raise my hand. So.
Okay, go ahead.
Right, thanks. That's very nice. This what you have done, and also, I mean, goes in the direction of automatizing operations. That we well know it's a very hot topic for whoever is doing experiment operation. So I'm wondering how you can, I mean, how we can use this machinery for other to monitor other features, like, I mean, experimental services on VO boxes, on so on and so forth. I mean, we have a distributed infrastructure, for instance, that we want to monitor its service that we want to monitor. I mean, I guess my question is, do you plan to put your work and development somewhere so that others can start working from it?
I see what you mean. So firstly, the main let's say cornerstone that this project was standing on was that the application has to be somehow load balanced. So if you have just one VO box per site, or maybe even two, I don't think that's sadly enough. On the other hand, if you have a cluster of, say, database servers, it would be perfectly suited for that, especially if they are more or less loaded the same way. Now, we were planning on trying this approach out for different applications, but sadly we haven't had the time yet, but it is indeed planned. To answer your second question, now, the idea is there, and it turns out it works, and it might work quite well. The work I did was very specific to the Monit infrastructure. So the Monit team obviously has access to all this work, and maybe if you're at CERN and if you want to try it out, they will let you, or just contact me and I'll arrange it somehow. But from outside CERN, I'm afraid that most of the work will have to be done customly for your monitoring infrastructure, whatever that might be. So yeah, but it turns out if you do the work, you might actually see some good results.
No, that's exactly why I asked, because in LHCb we are doing a lot of collaboration with the monitoring team, and so, I mean, if this can be extended to this kind of studies, this would be great. Okay, thanks a lot.
Okay, yeah, just let know the monitoring team, or shoot me an email and we can arrange something.
I guess the other thing which might be generalizable from it is which are the ML algorithms which can best detect the anomalies, and that would be very interesting to know. That could be used by other people in other infrastructures. Anyway, very good. So thank you, Martin, and also to Andy and Davide for this nice session. So we'll go to the break now, and then we'll resume at 10:40 Prague time. So see you in a little bit.
Okay, thank you.
Okay, so we get ready to start up again. So Mikhail, maybe you share your screen.
Okay, so I hope you can see me and my slides.
Yep.
Then let me know when I can start.
Okay, that's gone 20 to 11, so I think you can take it away.
Very well, so good morning. What I will be talking about is basically overview of Atlas distributed computing and where we stand between run 2 and run 3 with outlook to high-room LHC, and with a little bit of focus on what these changes can imply on analyzers. So let's start with a bit of introduction. I think I don't need to spend a lot of time on introducing Atlas experiment. It is a big experiment, both in terms of size and in terms of collaboration size. So with thousands of people participating, also the computing size needs to be significant. So a bit of introduction of Atlas distributed computing. It manages resources on 100, 150, maybe more sites, which represents about half exabyte of data and more than 400K CPU cores, and it runs non-stop. There is a little bit of split of sites depending on their capabilities. So you can see it on the map. There's TU0, which is CERN, and that is largest resource and also has all the detector data, and they are archived on tape. There are T1s, they are usually the largest computing centers, and they also usually have tape and store the second copy. Then tier 2s, which are smaller, not always that much smaller computing sites, and then tier 3s, which are small sites, sometimes only used for local users and local analysis. For the components of ADC, we have workload management. This is basically how to submit jobs to the resources. So process is a component which organizes jobs into tasks into requests, and manages this whole workflow. And then there's Panda Jedi, which deals with submission of these jobs into various resources. For data management, we have Rusio, which manages the storage, the access, the replication, the edition, everything. And it seems that Rusio is becoming more or less standard in high energy physics community, as many other experiments other than Atlas are using it. And then there are additional components like information system, which is now AGIS and so to be Greek. We have monitoring and analysis platforms, etc. For current status, as I said, we have about 400K cores. On the plot, you see the usage from the beginning of this year. So most of the resources are coming from Grid, which are WLCG grid sites, but then there are also cloud resources, and this also includes a 0.1 farm, which has about 90,000 cores. And then there are HPCs, Boeing, etc. For storage, as I said, we have about half exabyte of space, which is more or less split half and half between tape and disk. On disk, majority of formats are for analysis, which I will show later. And the problem is that disks are always full. And most of the data are primary copies, so it means that they cannot be deleted. And there's only a limited amount of cached secondary data which can be deleted if it is necessary. We have various mechanisms of coping with this. We delete unused data, and old analysis formats if they have newer versions, etc. For the run 3 and especially high Lumi LHC outlook, as everyone know, I guess the performance of LHC is supposed to improve a lot, so we expect to have about more order of magnitude more data, which needs to be stored, processed, analyzed, etc. So the problem is that the computing budget is assumed to stay flat, and the additional resources we got from technology advancements, this is decreasing. You see on the middle plot, this is price over performance evolution at CERN. So like 10 or 15 years ago, it was decreasing quite nicely as you got more performance for the same amount of money. But recent times it is slowing, or it is actually increasing sometimes. So you need to pay more to get the same performance. On the right, you see predictions for CPU and disk usage. So I could say that for run 3, we could manage to run with the current system, but for high Lumi LHC, we need aggressive R&D to be able to fit with available resources. So I will give you some examples of R&D, like there's new analysis model planned, improvements in software, tape usage, access to compute, etc. So let's start with the analysis model. The current model is there's a centralized data reduction system that is using output of reconstruction, which are AODs, and produced so-called DAODs or derived AODs. And the content is created from AODs. You can remove object or variable or even whole event or add something. And this is something that can be tailored for specific analysis by analysis teams. On the plot, you see that AOD and DAOD represent like 3/4 of all data on the disk. So another point is that DAOD overlap a lot, so this is causing a heavy footprint on the disk. To solve this, there's new analysis model in preparation, which proposes 2 new formats, which is DAOD Fizz and Fizz Lite. Fizz having about 50 kilobytes per event and Fizz Lite about 10. Of course, not all analysis can be covered by this, but majority should be using these formats. And also for analyzers, this causes advantage that with smaller size, we can keep more copies, so the availability for analyzers will improve. On a side note, it is planned to be rather flat, so it can integrate better with Python-based analysis ecosystem. And at the side note is there's investigation on application of lossy compression, which could save space, but it's tricky to not affect the physics in the input files for the analysis. For software, start with event generations. So this is expected that next to reading order and next to reading order precision will be needed. So that means a lot of computing resources will need to be spent. With event generators, the problem is that they are not product of collaboration. So we do not control them. We have kind of influence on what can be done. So there are a few ways we can decrease the resource usage. So we can choose quite carefully what kind of physics we will generate. We can bias the event generation as a function of kinematics, so that you don't spend a lot of CPU time populating some extreme corner of phase space. Uncertainties from scales and PDFs can be done by reweighting, so you do not need some large Monte Carlo to do that. Also, as this is experiment independent, we can share them with other experiments. In this case, it would be probably mostly with CMS. For simulation, which is modeling of interaction of particles with the detector, there are many these projects in Atlas and Jan 4. We have so-called full sim and fast sim. Full sim is based on Jan 4, and fast sim is based on parameterization of calorimeter response. So on the right, you see that most of CPU usage is for full simulation, but as far as event processed, the most of them coming from fast simulation because they are just so much faster. So the ratio between full simulation and fast simulation needs to change, and we need to use more of fast simulation. For digitization, which is modeling of output of the detector, the plan is to use pre-mixed pilot data sets, and then the hard scatter events will be digitized and then kind of overlaid on the top of these pre-mixed events, which is considerably faster, has better I/O, and scales better with luminosity. The problem is that these pre-mixed events need to stay on disk, and this could mean a lot of permanently blocked storage. As right now, I don't have a really number of how many petabytes this can be, but it could be significant. For reconstruction, which is creating of high-level objects, I just can make general remark about ACTS, which is common tracking software, which is open source project to develop tracking software. So improvements in compute, first I need to say a bit about how we can split the jobs in Atlas. So there's production, which is basically running from raw or event generation to AODs. And this is done centrally and under control of very few people. And then there's analysis, which analyzes that are using the AODs usually. So on the plots on the right, you see that as far as CPU usage, this is a small amount of resources used. But in terms of files used, this is dominating because the analysis are IO heavy. And currently we are going into process of grant unification. I guess it's almost solved, which is basically a way to unify access to sites, so we can decide what is the share between analysis and production, and this can lead to increase in utilization for analysis at one site and decrease in other, depending on availability of input data. And by this, analyzers can get faster to their input and get a faster turnaround for the analysis. Another thing is containerization. So right now, almost all jobs are running inside a container, which is Singularity, but there's plan for, and work is going on user-based containers where you can all your software you need inside, and you don't need any complicated setup or ask someone to install something or for data preservation. Another
3 minutes more, Michael.
okay. Another thing are Jupyter notebooks, which where you can do interactive analysis in Python, either on some horizontally scalable cluster or batch system, if it would allow kind of specific scheduling. For usage of disk, there's data carousel project, which is a sliding window approach to orchestrate data processing. So basically, you stage only data from tape to disk, which are needed for currently running tasks, not like all year or whole run to data. And this was tested and works rather well with out of 18 petabytes of run to data, was only a small amount always on the disk. So to summarize, high LHC especially, but also run 3 will be very challenging. The current computing model is not sustainable for high LHC, so there are many improvements needed by the ADC and aggressive R&D to make to store the data, process them, and make them available for physicists, and also to give them means to analyze them. So I give example of analysis model, software improvements in access to compute or in disk and tape usage, etc.
Great, thank you very much, Mikhail. You covered a lot of ground there. So let's open the floor to questions. We certainly have time. Nicole?
Hi, Mikhail. Thank you for the talk. In terms of fast simulation methods, you mentioned that your biggest adoption is the parameterization of the calorimetry system.
Mm-hmm.
This is obviously slightly different to LHCb in terms of what we're using. I mean, are there other ones you're using as well, or is it mainly this?
Well, it's supposed to be the whole chain, fast digi, fast recall, and fast same, and in several versions. So it's I don't really know enough details to give you example of parameterization, but there's a lot of R&D there.
Okay. Cool. Thanks.
We certainly have time for other questions.
Yeah, I was curious about your derived ALD reduced format, I mean, FIS and FIS-Lite. I mean, how do you accomplish this? Do you foresee a single structure, or do you foresee selective persistency according to the analysis that is going to use those data? I mean, how you plan?
The content of FIS and FIS-Lite is actually still being investigated, and it is, I think we have found some first versions, and it's being evaluated by analysis groups if the content is okay. So for some special analysis, we might need another DAODs or even use AODs for analysis. But for, let's say, normal analysis, these two should be enough. The difference would be, I guess, the AOD FIS could have some more data on trigger or calibration, etc.
Maybe
if I may comment on this, if you do a reduction of this size, I think you have to do on both ends. You need to work on the technical side, on smarter storage, compression, and of course by cutting out things that are not used or can be recomputed. So I think this is really a mix of actions that need to be taken.
Thanks, Andy. James, do you want to make a quick comment on this?
Yes. Yeah. So, I mean, the main difference between this model and the model we used last time is that previously we had all these different formats, 84 of them, which were skimmed according to the needs of the analysis groups. What we observed is the per event content was roughly the same. And these were the variables that were needed to do the apply calibrations or run various systematics. So this new, and as Mikhail said, because there were so many of them, particularly with Monte Carlo, they would very strongly overlap. So we're writing out the same data over and over again. So these two new formats are not skimmed. The first one, DAOD-FIS, it contains all of these variables that are required for applying calibrations, etc. And that's the one that we will generally use in run 3. It can be skimmed centrally if necessary for those groups who only require a very small number of events. Now, FIS Lite, the idea there is that it's pre-calibrated, so we can throw away most of the variables that are needed to apply the calibration because it's already done. This is going to be used in primarily in run 4, but of course it needs quite some commissioning because it's a much more complicated way of working on such a small format. And then, yes, finally, as Mikhail said, certain specialized analyses will still need extra information which is not available in this DAOD-FIS, and they will continue with the model that we roughly use in run 2. Okay, I hope that was added a bit of extra background to this.
Yeah, thanks a lot.
Okay, thanks very much, James. Well, I think we should move on, but remind people that we do have Mattermost if you want to carry on the discussion. So next up is Nicole, who will tell us about the evolution of the LHCb offline computing towards run 3.
Yeah, let me just try sharing my screen. This one. Okay.
We'll try and make it full screen so it's bigger.
Yeah, let me just move this out of the way so we don't have a problem with last time.
Yeah, that's very good.
Okay, excellent, great. So yeah, I'm Nicole. I'm a postdoc at the University of Bonn, and I'm very happy to be talking about the evolution of the LHCb offline computing towards the run 3 upgrade. So just a recap of what our LHCb detector looked like in run 1 and run 2. As you know, LHCb is a forward arm spectrometer specializing in the decays of beauty and charm hadrons. And on the right, you can see a plot of our integrated luminosity throughout the years of run 1 and run 2. And in total, we collected 9 inverse femtobarns of data. And as you'll see from the many talks in this conference, we're fully exploiting this now. But obviously, this talk is focused on the upgrade. And we expect an instantaneous luminosity increase of factor 5. And you can see the various subdetector changes we're making. But from a computing point of view, the big change is a new fully software trigger. And the big news is that our HLT1 will run on GPUs. So in essence, we're expecting a data rate increase by factor 30 in the upgrade compared to run 2. And this talk is going to talk a little bit about how we deal with the challenges that come with this in the offline data processor. So we can start with the data flow evolution, looking at the persistency models that we had in run 2. So when we trigger on an event, what parts of the event do we actually save? So the minimum, of course, you can save is to just save the reconstructed objects involved in the trigger decay candidate. So if you're triggering on the signal of a D0 to K pi, you just save the reconstructed K pi objects. And this is what we call a turbo stream. Sort of then moving down, sort of increasing the amount we save in each event, we have turbo selective persistence, or turbo SP, where we can save additional reconstructed objects. So in the case you see here, we're saving objects that come from the same primary vertex as our signal decay. And this is customizable. You can choose exactly what other parts of the event you save. And then at the other extreme, we have the full, what we know as full stream, where we save the whole raw event. And this was actually the only thing we had in run 1. So all the run 1 analyses used the full stream where we saved the entire raw event. Now in run 2, most of the physics did use this full persistency model. And of course, because we're saving the raw event, what this meant is that the raw event came out the raw data came out the trigger, and it would need to be reconstructed offline. And then because of the event size still being large, it then had to go through this stripping step, we called it, which is just a slimming and skimming of the data, such that it could be small enough to be saved to disk, where of course our analysts can use it. But we did have quite a good uptake of Turbo and Turbo SP, mainly for our charm program. And here, obviously, the reconstructed objects were taken from a trigger. And then there's just a very minor file reformatting need to be done before we can save the data straight to disk. This is why it's called Turbo, of course. Now, in the upgrade, due to huge developments on the reconstruction, alignment, and calibration of our subdetectors, all the reconstruction will be performed online. So we can sort of get rid of this offline stages here. So of course, we will have our Turbo and Turbo selected persistence, which again will be immediately available on disk. Now the full stream will save the full reconstructed event. So in principle, the raw data can be removed at this point. We have a third stream known as TurCal. This is used for calibration purposes, not physics analysis as such, where we save the full reconstructed event and then some raw detector information for calibration purposes. So with this new persistency model, we can't save, of course, all this HLT output straight to disk. So we want to utilize cheapest tape storage to take the bulk of the bandwidth, and that really is basically the full stream. And we're going to have to rely on a central offline slimming and skimming to get this data small enough to go to disk. So you can see here the two models that we have. So the default model is for the Turbo or Turbo SP model, and all physics that can should obviously adopt this model, where the event size is small enough such that it can be saved to disk. The sprucing model is for the full and TurCal streams, where between the data being saved to tape and disk, we have this further offline stage of data reduction and selection. The key design choice here is that the selection framework in the sprucing is the same as that in HLT2. That has a number of benefits, but ultimately you're dealing with the same selections online and offline, which is beneficial for many reasons. So the use cases we see for the sprucing model are things like topological triggers, where you have to save significant amounts of the event, inclusive triggers, and of course for use in data mining, so which we profited off greatly in run 1 and run 2 analyses. In run 2, we did actually have 29% of our physics rate already going to turbo streams. So you can see in this table here the sort of split between where our physics was going to which stream. But in the upgrade, of course, as I said, we've got a luminosity increase of factor 5. The HLT efficiency will increase as we removed our level 0 hardware trigger, and the raw event size will increase just to the number of primary vertices in each event. If we were to not change our sort of stream split with our physics, we'd have a HLT2 output of 17.4 gigabits per second, which is obviously unsustainable. So we're relying on a large fraction of our physics channels moving to the turbo model. And on the left, you can see our baseline model here. So we're looking at 73% of our physics going to turbo stream, which gives us an output data volume of 10 gigabytes a second. Now, this obviously requires a huge migration of physics selections to the new HLT framework. And this effort's ongoing, and it's largely led by the physics analysis working groups. The key is now that these selections obviously have to be optimized for speed because they'll run offline. They'll run online, not offline anymore. The physics that can't move to turbo, for whatever reason, will obviously follow the sprucing model. And this slide really shows what the workload that the sprucing will have to do. So on the left, you can see the event rate, and on the right, the throughput for what comes out the trigger, what gets stored to tape, and what gets stored to disk. And you can see the event rate is dominated by the turbo stream, but the throughput is hugely dominated by the full stream just because of the event size. So the job of the sprucing is to get the full bandwidth from 59% to tape storage, and then reduce it to 22% of the bandwidth going to disk storage. So that's the workload that the sprucing has to deal with. So moving a little bit further down the analysis chain, obviously real data dominates our disk storage, but simulation dominates our CPU needs. And in fact, it takes 90% of our total offline CPU resources. So decreasing the time required to simulate our Monte Carlo is crucial if we're going to fully exploit the larger data sets in the upgrade. And indeed, we already have measurements that hint at standard model tensions, having systematic uncertainties that are dominated by our limited simulation statistics. So fast simulations are obviously crucial for us in Run 3. And already in Run 1 and Run 2, we've had a really successful adoption of some of these. So you can see in this pie chart here, 38% of our simulation still goes to full simulation, but 53% now uses redecay. And LHCb has really taken up redecay in a big way. It essentially reuses an underlying event, maybe 100 times, but generates and simulates a new signal decay for each event. So, and you can see speed increases of a factor 10 to 20 here. There is a dedicated talk to this, talk 516 by Adam Morris, about how LHCb is using these. So moving on to sort of the data tuples that our analysts use. In Run 1 and Run 2, analysts created their tuples individually using Ganga. This didn't scale well, and it's not going to scale well for Run 3. Thousands of jobs, faulty jobs can be submitted instantly, and 10% of our user jobs fail. It's very time consuming, on the order of weeks to produce a Run 1 2 tuple set. And you have to sort of babysit these, you have to resubmit the failed ones manually. And there's no analysis preservation sort of inbuilt into the system. So in Run 3, we want to move to submitting these jobs centrally using the Dirac transformation system. And we've termed these as analysis productions. And our Monte Carlo is actually already produced this way. And the nice thing is it doesn't require you to babysit the jobs, as the Dirac transformation takes care of this for you. In the prototype, we've developed the jobs can be tested automatically upon a merge request using the GitLab CI. The job details and logs are automatically preserved either in the bookkeeping, or the logs get sent to EOS. There's a very nice automated error interpretation and advice for when things do go wrong. And as you can see, the results are displayed like this on a web page, where you have all details about how a tuple was created, and then this is obviously preserved for forever. To make our tuples, we use tuple tools, and these essentially just create and save a number of variable branches for typical use cases. So an example is tuple tool track info. The problem with these is they're very easy to implement, a couple of lines, but it can add a lot of redundant branches to a tuple. And for a single Run 1, Run 2 analysis, we can have anything from 500 gigabytes to 10 terabytes for the user to look at. And these tuples tend to only be used for one analysis. So for Run 3, we're looking at a major redesign of these tools to try and minimize the redundancy and make this a more customizable thing. Like the rest of the LHCb uses a wide range of tools, obviously C++, Python, and an uptaking of NumPy, pandas. Custom user environments, of course, for use on the distributed computer system are limited by the CVMS distributions, but we're experimenting with providing analysts the ability to install custom Conda environments on CVMS, and also making use of singularity containers, which we're already using to run legacy applications on the grid and looking to expand this. A quick note on our heterogeneous resources. As we know, from the last talk, the grid, we have 1 million CPU cores at over 170 sites. Most of these sites have no GPUs yet, but there is a push towards high performance computing centers, which could in principle provide large GPU resources. Also, as I said, our HLT1 will now run on a GPU farm. We'd like the ability to utilize that farm during detector downtime for jobs much like we do our current HLT CPU farm when LHCb isn't running. But to do this, we need to have a lot of development in our significant payloads to make them actually be able to run on GPUs. And you can see what jobs we run by job type on the right here. And user analyses are beginning to utilize GPUs. So for instance, use of TensorFlow for machine learning and fitting very complex amplitude models. But actually, user jobs is quite a small share of our CPU. And indeed, most of our CPU is dedicated to detector simulation. But obviously, GM4 doesn't have GPU compatibility yet, but we're aware work is ongoing outside LHCb on this. And then finally, obviously, GPU batch cluster at CERN, which will help us develop and run our GPU workflows. So just a final note on our new data processing and analysis project, or DPA project. Obviously, as I've said, run-free offline data volume necessitates a much more coordinated approach to the offline data processing. And we now have this DPA project, which has 5 work packages addressing the various issues that I've mentioned in this talk. And this project will work very, very closely with the computing team to try and coordinate these efforts and really make sure we can handle the increase in data volume. So in conclusion, obviously, like all the experiments, LHCb will have to process much more data offline. And we're progressing well to meet these demands, including the treatment of our event persistency models and our sprucing, essential offline data processing. We've already adopted fast simulation, and we're going to try and keep pushing that forward. We want to push initiatives to use accelerators, and we have the creation of this new project to work in collaboration with the computing team to really coordinate these efforts. Thank you.
Thank you very much, Nicole. So that was a very nice overview. We certainly have time for some questions. So maybe I'll ask one. So we talked about initiatives towards the use of accelerators.
Mm-hmm.
We talked about the HLT1 moving to accelerator for run 3 in LHCb. So let's assume that you did get a bunch of GPUs out there on the grid. Would you actually be able to use that usefully today? And what would the next piece of software, if you were to put a big star on it, this is the next bit that I want to work, what would that be?
So as I said, we have to put quite a lot of development into making our stuff work on GPUs. The main one would obviously be the full simulation, but obviously this is slightly outside of LHCb. I mean, we do have quite a lot of analyses now. You know, we have amplitude models with 100 fit parameters and, you know, hundreds of thousands of events. And without these TensorFlow type things, that they would be impossible. So I think they're incredibly useful at the user analysis level already. Yeah, that's what I would say. We would definitely use them for user analysis.
If I can add briefly to this, from the infrastructure point of view, we are using Dirac, and there have been some prototype work in using a cluster, GPU cluster in Manchester, where jobs have been submitted. But you have to tailor this very well. I mean, it's not a generic submission system for GPUs. So if you have an application that can run on GPUs and you can target a single site, you can do. But of course, it's not more than a prototype. This was done within the Grid PP Dirac installation.
Thanks, Concepcio. James?
Hi, yes, so thanks for the nice talk. So I just wanted to ask about the analysis model that you described on slide 14. So I think every experiment has gone through this this realization that the creating n tuples from direct user analysis is something that doesn't scale so well. I was wondering how big are the data products that the n tuples are being made from? So are they're sort of large output of reconstruction level, or they've already been significantly reduced at this stage, or?
So from run 1 and run 2, these tuples are made after the stripping step. So they're made from the output of this step. So they're already quite slimmed down. Yeah.
And how many different formats are there then that after the stripping? It's
after the stripping, the output of the stripping is either DST or MDST. Those are so if you're making tuples, basically you're using a DST. Yeah.
Right. So the realization is that even running on these significantly stripped down formats, running the user analysis is still essentially not efficient enough to sustain run 3 analysis. That's the conclusion.
Yeah. Even now, it takes on the order of a couple of weeks to take the stripping output to a tuple. Yeah.
Okay. Thank you.
Okay, thanks very much, Nicole. That was a very nice talk indeed. So let's move on to actually the last track, which is going to be on resource provisioning and workload scheduling in CMS. And Antonio is going to give us that talk. So if you can set yourself up, Antonio.
Yes. Okay.
Yep, that looks perfect. So
okay, I'll get started then. Yeah, so I'm going to talk about basically the CNS submission infrastructure and the global pool of resources, how this pool has been expanding and becoming more complex with time, and how it will be even more so going into the future. I will describe some ongoing and future work, which is modifying the aspect of this submission infrastructure and provide some conclusions. So the summary, the submission infrastructure, we'll refer to the submission infrastructure itself and also to the submission infrastructure team, which is leading this infrastructure, of course. So we as a team within CMS experiment, what we do basically is run the computing infrastructure in which all processing, reconstruction, simulation, and analysis of physics and data takes place. So in order to do that, we manage a Condor pool, which is created via Glide WMS submission of pilots. And then, of course, our main concerns is also to communicate the CMS priorities to the development teams, which provide us with these tools, Glide WMS and Condor, of course. Our activities basically are divided into, of course, fighting the current problems, the current fires, and getting the pool to run stable, preparing for future scale and also anticipate future requirements, and integrate new resources types and diverse job submission methods, different than what we have presently. This is the classical view of the pool. It has 2 layers. Basically, on one side, there is the Glide WMS layer of the pool, which is the site that creates the pool, and the other part is the Condor pool itself. So in creating the pool, there is a front end which queries the job scheduler nodes, where basically all the jobs are accumulated, and on the basis of this job pressure, pilot jobs are submitted onto the resources, be it Grid, Cloud, or whatever. Once these pilots, which are all multi-core, by the way, start, they launch the process, which is a Condor Starty. This Condor Starty connects to the central manager of the pool. And of course, this creates the pool itself. And then the negotiator can do the matchmaking between jobs and resources. This is the usual pilot build model of a pool. Now we have to do basically our most important task, of course, besides building the pool, it's handling the workloads, scheduling. So in that we have to consider that we have different type of requests, data processing, Monte Carlo generation, detector data reconstruction, etc. And also all these requests have different resource requirements in terms of number of CPUs that they have to run. Maybe they need accelerator, or they are prepared to run on accelerators, amount of memory, disk and network I/O, etc. So each job has requirements. So we have to do the scheduling, a good scheduling of all these types of requests. And of course, what good scheduling means can be interpreted, and it's usually interpreted in a number of ways. So we have to use all the resources efficiently. We have to respect the fair share between the groups. We have to respect the prioritization. We have to minimize job failures. We have to provide flexibility in order that somehow, at some point in time, we can be able to handle some uncommon requests. So, for example, very high memory requests. And of course, in the end, anything that is related to the TF0, so to the data processing, directly data processing, needs to have the highest priority at CERN. So all these interpretations of good scheduling, of course, have a big overlap, but they are not exactly the same. And we have to do our best to try to ensure that all these goals are reasonably covered, and even under evolving scenarios through the years. So some results on how well we do this effort in scheduling. First plot on the top is actually showing the utilization of the resources. So it's all the resources in the pool are utilized at 95% in general. This is the typical utilization of the pool. These other plots are showing how well we do the mix of the different types of requests and how we satisfy the different customers, so to speak. So here you can see the fair share between analysis and production with the same definitions used before by the Atlas colleagues. And then, for example, if you go into the production, of course, you have the different teams analyzing data for different physics purposes, and you can distinguish how this evolves with time based on priority, and we're satisfying, let's say, B physics, Higgs, top analysis, etc. So yeah, we have good scheduling, so to speak. We have a big pool, and we have to handle it, even if this pool has been growing through recent years. So over the past 3 years or so, the size of the pool has basically doubled. This is mostly driven by the increasing requests during the LHC Run 2. The Condor pool right now, it's around 250,000 cores, 300,000 cores in the peak when we include also the CERN resources, which for stability reasons are installed in a separated pool from the main global pool. And it's also worth noticing that during the Run 2 and Long Shutdown 2, we have been progressively adding more opportunistic or non-plex resources. So the most important in size is, of course, the HLT farm. So the HLT farm has been commissioned for opportunistic research for offline processing. And of course, we have been using this fully during the shutdown. So there is an increasing proportion of beyond pledge, also HPC and cloud resources in the mix. I will describe this a bit further later on. So this has been the growth so far, but of course, if we look into the future, especially for the high luminosity LHC, well, this is, I think, a well-known story. In the case of CMS, the current projections anticipate at least an order of magnitude higher in the processing needs than the current values. This is, of course, increasing due to increasing trigger rates and event complexity. This pile up 200, for example, working scenario. This growth factor is probably going to be reduced because there is still ongoing work on improving the software and improving the data formats. But nevertheless, we need to consider that there will be a substantial growth in the amount of resources, and how this will affect this submission infrastructure and the capability to do the workload scheduling. So one aspect is that we are still running, even though we're running multi-core pilots, we are still running some fraction of single core jobs, a non-negligible fraction of single core jobs. This is expected to be completely rid of, or at least very much reduced, so that by then we can increase the average number of cores per job and essentially do more work with less parallel tasks. Okay? Therefore, reducing the load on the infrastructure. Still, there are questions. How big of a pool will we need to manage when we have this increased amount of resources? How many scheduler nodes will we need in order to handle such a load and keep continuously feeding this pool? And also, again, consider that this growth will likely not come from created resources, but probably, most probably, from other type of resources such as HPCs. So in order to test the scalability of the pool and the stability of the infrastructure, we continuously run certain stress tests on the pool. So we are continuously reassessing the improvement that we get from both Glide WMS and the Condor software packages. Of course, we will let's say, we try to break the pool, we try to see where is the maximum load that it can achieve while still retaining high efficiency in the utilization, which is what we want to do, of course. So we have been pushing for the highest size of a single pool, trying to count the maximum number of jobs that we can run. And we have observed that we can get up to 400,000 concurrent running jobs. Mind you, this is running jobs, not CPU cores. So at the present value, we have 2 cores per job on average. So this would be this double amount in total amount of CPU cores, which is a big increase with respect to the current number of CPU that we handle. We have been exploring also the submission rate limits of the scheduler nodes, and it's closer to the hertz than to the 10 hertz values. Okay. So yeah, we need to be careful on keeping the scalability of the pool. Also because we have to deal with this other element, the increasing complexity in the pool. So from the picture that I showed before of a single pool, in fact, we need to go to this rather cumbersome picture in which we no longer have a single pool, but we have several of them. The global pool in the center is the main one. Still, it handles the majority of the resources, but we have additional accessory pools which handle specialized resources too. And we have distributed scheduler nodes, both at CERN and also at Fermilab, and they are connected in different ways to access all the resources in the pool. Most of the resources are still acquired by submission of Glide WMS pilots, but now we have also vacuum model instantiated slots, for example, with this DODAS project, which are directly joining the pool. We also have Boeing resources, these opportunistic, which are kind of VMs, the DHLT VMs connecting directly to a pool, etc. And of course, the several components of HPCs. So coming to HPCs, why are they important? Well, we know that there's going to be an increase in usage of HPC resources, and this is because there is growing funding for HPCs. They are different countries and funding agencies are pushing to deploying the exascale or near exascale machines. And the same funding agencies are also pushing higher physics communities to make use of these resources, because of course we have the computers, so we better use them. That is interest in our part as well, because we not only use these resources as CPU, but also we will have access to different technologies potentially. For example, GPUs, which are going to be employed in HPCs. So all in all, the HPC contribution to the future of our computing, it has been acknowledged to be an integral part of the WCA strategy towards the Helmut University LHC. And this is from a talk by Ian Baird last autumn, where you can see the HPC included explicitly in the picture. So again, the same picture I showed before, the complexity of the pool, and now you can see I'm explicitly noting where we get and how we get HPC resources included in the mix. So the main component is still right now is grid-like HPC. So we basically submit pilots to ASI. These pilots get to start and then join the pool. This is the case, for example, for CSCS, Switzerland, or Cineca in Italy. We can think of instantiating vacuum model slots in HPCs as well. And the other major component so far for us is the HEP cloud. So the HEP cloud is functioning as a federated pool to our global pool, but this is actually decoupling the management from CMS directly, and it's actually managed from Fermilab. So Fermilab HEP cloud is incorporating not only the own resources at Fermilab, but also several HPC sites in the US. And we have access to these sites in the US via HEP cloud. So some words about dynamic resources integration. So a lot of work has been done recently in the integration of such resources into the global pool, and more in general for CMS use. So HPCs, we are now submitting pilots to Cineca, and we have also HEP cloud slots as well. Cloud we are submitting to sites, and these sites are passing on as an extension of the site. They are passing on these pilots onto cloud resources. For example, we have Azure on CERN, and we have also Amazon as an extension of PIC, the one in Spain. We have been using, sorry?
Just 3 minutes more.
Yes, thank you. We have been using NEO cluster. For example, you might have heard of this beer resource as CERN. This is batch on NEOS racks, let's say. And we have also access to extended research or university campus resources, such as, for example, in KIT or Purdue University. And finally, we have the volunteer pool for CMS at home. So these two plots are showing basically all these components, how they are already providing resources. So you can see, for example, here, the main component in this CERN beer running, Kenaf Cineca also contributing with several peaks. And on this part, you have the HEP cloud elements with several HPCs in the US, mostly NERSC, but also Comet and Bridges. Okay, an important aspect is that in order to use many of these resources, which are non-standard, we need an enhanced workload and two-resource matchmaking. So this means that we need an expanded description of both the jobs and the resources. For example, we know that some of these machines are actually running on KNL nodes, and this radically modifies the running time of the jobs. So we need to make additional selection of what type of jobs can run in these resources. Or for example, maybe some of the resources lack a direct access to a nearby storage. So we only can run simulation tasks. So we need to go a bit farther in the matchmaking of resources, of resource to resources for this type of machines. A hard case, just to mention it, we have the Barcelona Supercomputing Center. It's a big machine in Spain. It's the biggest machine in Spain. It's approaching it's going to be funded to approach the nearest exascale cluster in a year, principally. And the main point is that it's very hard environment because they have many of the elements of communication that are needed for a pilot to work are basically closed, shut down. So we need to find alternatives, and we have been working, the PIC team, of which I am part, and the Condor team, we have been working on a project to enable network isolated nodes to be incorporated into a pool for CMS use. As I mentioned, and we have discussed, a lot of the resources in the HPCs are going to be GPUs, and we need to be prepared for that. I want to call your attention to the fact that Glide WMS and Condor are already providing us with tools to manage GPUs. For example, we have this tool for Condor GPU discovery that can run in our pilots. And we also have the proper, let's say, language in order to do the matchmaking, because jobs can already specify if they require GPUs or what type of additional requirements they have, for example, the type of GPU or their capacity. All our jobs are executed in Singularity containers. they're all running in these containers within our jobs. And we have specialized singularity containers for TensorFlow workflows. And these are distributed by same file system and supported by OSG. So CMS already has a small fraction of GPU resources in the global pool, mostly in the US sites. And also we have a method of submission of jobs, CMS Connect, which is a lightweight WM entry point and mainly for analysis jobs and already supports requesting GPUs. So we are starting to get prepared for the use of GPUs, let's say. So very quickly, ongoing and future work. We maintain the goals and we continue working in this direction for submission infrastructure. So the integration of grid resources, non-grid resources, excuse me, and the support for GPUs. We have been working a lot on improving our monitoring, of course, in order to do our better job and also provide better feedback to the developers and where things are breaking, where we try to push too hard. Improve scheduling. For example, we have been thinking about tuning tasks after they have been modified. So this is modifying after they have been submitted. So this is modifying the job resource requests. We are thinking and we are starting to work on deploying the infrastructure, not based on bare metal or VMs, but based on Kubernetes containers. And we continue running the scalability and stability tests. For Condor, we are interested in trying, and we are already starting to test token-based authentication. And it's interesting for us also the concept of jobs and resources, because this is potentially reducing combinatorics and allowing the infrastructure to grow. Glide WMS, we continue using Singularity. We now move to native Singularity support from Glide WMS, and it's an important element here to allow the configuration of pilot entries from the CRIC information. So CRIC is the new information layer that CMS has adopted, and we are working on integrating these two elements. Just as an example of the very nice flexibility that we have in our pool, we very quickly were able to integrate folding at home jobs to run against COVID-19 in our pool. It was a matter of hours, let's say, to wrap the folding at home element into some wrappers for Condor and submit them directly into the pool. So this not only we intend to have helped in the fight against COVID-19, but it also demonstrated nice things about the pool. Lessons were learned about how we can seamlessly handle non-CMS applications and new applications, and this will be useful for the future CMS processing. For example, in backfilling grid slots with lower priority CMS jobs, which is what we did with the folding at home tasks that you can see here at a very small fraction of the pool, but nevertheless, they are filling the holes that are left by our main production and analysis workflows. So in conclusion, what we deal with is the resource provisioning and workload scheduling for CMS. Good scheduling has multiple criteria, and we have to work to cover all of them or most of them. CMS has been growing in the resources and expects increasing scales onwards, looking to the future, and more complex mix of resources. So we need to be prepared to access different resources other than that grid and to be able to use them. Like I mentioned, these GPUs. We are working hard always to detect potential bottlenecks into the infrastructure and to assess the scalability of our tools. So yeah, we work on the integration on non-grid resources, especially HPCs, and in particular for sites such as the Barcelona Supercomputing Center, which is a hard environment. And we are integrating many of these resources already. Yeah, so the ongoing future work is dedicated to continually providing CMS infrastructure with further flexibility and reach. And as usual, I want to finish acknowledging the effort and the support that we get from the Glide WMS and Condor developer teams, as well as CENIT, of course, for the support and collaboration. That's it. Thank you.
Yeah, thank you very much, Antonio.
And apologies, I ran a bit longer.
Well, you were also the last speaker, so.
Okay.
Okay, there's a question from Jiri, so we could maybe take a couple of quick questions. Thanks. We can't hear you, Jiri.
Is it better now?
Yeah.
Okay, so I would like to ask you about continuous scaling tests. You said that you were running more than 400,000 concurrent running jobs. Was it on some special test bed where you run several hundreds or maybe thousands of jobs on one server, so you just need few servers, or was it on the real infrastructure? The question is, if it was only on some test infrastructure, how are you sure that in the real life, where round trip times to many sites is much higher, that it would behave the same as for this test?
No. We're actually distributing the load over the whole grid. So what we do is we create these Uber glidings. So instead of one core being one gliding, so to speak, or one batch of CPUs being one gliding, we basically overload our pilots to instantiate multiple starties. So they are distributed over the world. However, they have this additional multiplying factor. And of course, the jobs are dummy jobs in the sense that they don't produce an overload on the machines. But the fact that we are running sometimes even 32 of them at the same time for a single CPU. So it's distributed. So we are covering for that effect. Of course, we are not. We don't have 400,000 CPU cores at our disposal, or even higher than that. So it's a bit. We are mimicking that by this trick of the Uber gliding, but nevertheless, it is still a distributed infrastructure over the whole grid.
Okay, thanks.
Thanks, Antonio. Any final question someone wants to ask? Okay, I don't see anything. So my thanks to Mikhail and Nicola and Antonio for their contributions in the last of our session. And that, in fact, brings the Track 14 parallel sessions to a close. So I'd like to thank all of the speakers, both in this session and in the 3 previous sessions. And with that, I think we can let everybody go for lunch and very much hope that you enjoy the rest of ICHEP 2020. So thank you, everyone.
Thank you.
Thanks.
Thank you very much.
Bye-bye.
Bye.
Bye-bye.
Bye.